Hello, Yuri. Hello.
Hi, Gozhan. How are you?
Good. How about you?
Good, good, good. Let me turn a little bit more light on.
Yeah, I think I talked with Guilin, and your time was a mistake. And I was considering to send you an email tomorrow morning to remind your talk.
Yeah.
And
yeah, I think it's okay because, you know, okay, it's dangerous when it's 3 hours later here. I would just come 3 hours early and figure it out.
Right.
Okay,
No.
I just read your email. I probably made the mistake.
Yeah,
Sorry
it
about
was
that.
Pacific time. I know there are so many speakers in different time zones, so it's not surprising. Anyway, I just connected
It's
also to check
8:40,
that
right?
everything goes well. And I think pretty much already I also shared the program with my students. Some of them may be joining.
Thank you so much.
And you got an exciting lineup of speakers. So everything looks very good to me.
yeah, it is, you know, we're so happy to get such a strong supporter from all of you.
Yeah,
And
well, it's a pleasure. And I look forward to listening to some talks as well, yeah.
right. Yeah, it is. We got all those speakers, top quality scientists, scholars.
No, it is great. And I really look forward to a very productive event here. So,
Yeah, I think 2020, everybody's productivity would go down. At least that's me, including me.
oh, well, you know, like people sit at home, right? There may be a fewer experiments, more talking, more writing.
Right.
But I think also there is an opportunity for students to participate in many events over the world, to see too many prominent speakers that would otherwise I would not be able to meet. So there are pros and cons always, yeah.
Yeah, at least, you know, we don't need to travel across the Pacific Ocean, Atlantic Ocean, and check in hotel and argue with the receptionist which hotel room to stay.
Yeah, even so, I would say I feel like it's time to start traveling again. Meeting people, seeing new faces here. So
right. Yeah, hopefully everything will back to normal, and we still.
Well, I keep my fingers crossed. Things are getting better. I got my vaccine already, so I hope.
Oh, you already got?
Yeah, I got the second shot of Pfizer vaccine last week.
You already got a second. Gee, we don't get anything.
Oh.
Yeah, in Washington State, the teacher at the university is at the lowest priority list.
No, it's really not the university, just for the city of Philadelphia. So again, I think it's very different from place to place. Right. I hear from some colleagues that entire universities were vaccinated. They arrange for teachers, and some other even require students to be vaccinated.
Yeah,
so I think it's a very non-uniform throughout the country.
Yeah, it is true. If everybody get vaccinated, if I don't get, and I'm safe too.
Yeah, that's also fine, right? As long as other people around get vaccinated, yeah.
Right.
But that's not going to happen for another year or so worldwide.
Oh, hi, Stan. Good to see you.
How are you doing?
Have you got your vaccine?
I got my second one just over a month ago.
Okay, you're ahead of us, yeah.
Researchers at Binghamton were defined as essential workers last May and June.
Very good. Smart move from the State University of New York.
Well, it's just our campus, I think.
Yeah, okay, yeah.
They use their PhD students as guinea pigs for starting up the university. So they're all back in the labs early June.
Oh, is that true? Gee.
I wasn't, but they were. And New York's very efficient. I now have my vaccination passport, or whatever they call it.
Yeah, at UW, we are still discouraged to go back to campus. So this quarter, we are still stay online. So we're
we teach online too.
New York State.
Well, I think there's very few people, except researchers, working on our campus, but everybody's supposed to be back by August the 1st with a phase-in from June the 1st.
I see Professor Zheng Nanfeng launched in the system.
Hello.
Hello, Professor Zheng.
Oh.
Hi. Good morning.
Hi.
Yeah.
It's good evening for you, right? So.
I see who is. YouTube. 连州, you're online? Okay, Dongning is here and hello, Dongning.
So today's speakers all in.
Yeah.
Hello, hello.
Hello.
Hello, good evening.
Hey.
Welcome, and I saw you WeChat yesterday.
Oh, my WeChat?
Yeah.
I forgot. Did I do WeChat yesterday?
Or the year before yesterday, whatever you get the protest.
Ah, last week. You mixed the time last Sunday.
Oh, last Sunday. Okay.
Yes. I joined. Yes. Many people initially it was expected to be around 1,000 something like that, but actually came out several thousand, I think, because of the parade very long.
I see.
Yeah.
But I guess Montreal is still very cold, right?
Like today, actually, it rained a lot, but it's over 5 degrees. But a few days ago, 18 degrees.
Oh, okay.
You can see people on the street, they wear the shorts. You see what I mean? Yeah.
It is in Washington. Like last Thursday, I was on a ski resort. Quite some people wear shorts.
Okay. But you went to skiing? Because the snow all disappeared here.
Oh, we got a lot of snow. We got this year on the top of mountain in the ski resort, we got 15 meters.
That's a lot.
Snowfall.
Yeah.
And my last snow melted yesterday.
Oh.
We already started to play tennis outside in Philadelphia, so we are in a somewhat warmer weather. Even so, next week is again going to be cooler and rainy. Yeah. So it's still spring.
It's coming, right?
Yes. First flowers are appearing in our garden. So.
Yeah, today I saw a video, actually a black bear went to somebody's backyard and took over their hot jacuzzi and enjoyed a hot bath there.
Yeah, bears woke up, I think, recently too.
Yeah.
In mountains, yeah.
I even read news some days ago. A bear entered into a shop, market, to try to pick up food by itself.
Yeah, I think people stay home and the bear just got all over the place. They just take over the space.
Mm. But is your university fully open, like it turns back to normal? Your university?
Well, our university, we opened partially for the lab, for the graduate student, but the faculty members are still discouraged to go back.
Okay.
And, yeah, there are always some problems. And initially, I was thinking to stay in my office to chair this workshop. Mm-hmm. But then I look at the time; it will be like 9 or almost 10 o'clock in the evening. Mm-hmm. And I used to stay in my office till very late, but now I'm not that confident about my own safety. And then I just say, okay, come back home and session from home. Mm-hmm. It is, there are a lot of concerns. And so, but let me see. We need to admit somebody. It's not everybody got to admit it.
Professor Fan is not here.
Okay.
So shall we start now?
Yeah, we can start. So probably it's too early for the people to join us at the moment, or they are just waiting to watch the videos. Because I did not see many.
Yes, many people don't log in our Zoom room, but they watch the conference online through our live meeting.
Oh, okay. So it is they watch on the different platform.
Yes, because our capacity is very limited.
Okay. Yeah, that's great. So just
shall we start?
Yeah, let's get started. So what do you do? And I just start.
Okay.
All right. Well, let me see. Guilin wrote a welcome speech. Let me see if I can find the speech online and I can share with you. And yeah, I'm not.
Okay, I can create.
I'm not very good in reading the speech. Dear ladies and gentlemen, good morning, good afternoon, good evening, and good day, because we're all over the place. So everybody got your share. And my name is Guo Zhongqiao, and a faculty member at the University of Washington, and one of the co-organizers of this workshop. On behalf of Professor Yadong Li and the organizing committee, I want to welcome you all to this virtual meeting of International Workshop on Nano Catalysts and Green Energy. And this online workshop is sponsored by the Chinese Academy of Sciences, organized by the journal Science China Materials, and sponsored by Research Cloud. Dr. Guilin did all the heavy lifting in organizing this international workshop. And virtually everything was done by him. It has been a very difficult year. All of our lives have been impacted by COVID-19 epidemic. Although finally we see the light at the end of the tunnel, this is a different world, and many changes will last, if not forever. Just like any cloud has a silver lining, thanks to the advancement of communication and network technology, online virtual conferences provide an opportunity for scientists in different places of the world to meet, to share their views, and share their new research findings, and to exchange ideas online without the need to travel around the world. Today, through this workshop, we're truly honored to have some most distinguished scientists from the United States, Canada, Belgium, Australia, Singapore, and China to showcase new advances in the fields of catalyst and green energy. Topics include nano catalysts, electrochemistry, and energy storage materials. This workshop will have 3 sessions, one chaired by me today, and the other 2 sessions tomorrow chaired by Professor Yu Huang from the University of California at Los Angeles in the US, and Professor Xu Wang from Tsinghua University in China. Before starting the workshop, please allow me to take a couple of minutes to briefly introduce the journal Science China Materials. Professor Yadong Li is the editor-in-chief, and Dr. Guilin Wang is the managing editor, and I'm one of the associate editors. It is an international peer-reviewed journal, jointly published by Science China Press and Spring Nature. In the past few years, since its launch in 2014, it has been exciting and worthy journal, making it one of the prestigious journals in the field of materials science on an international basis. An important progress in its rapid growth is that it has ranked top 20 in the journal citation reports, with its latest impact factor reaching 6 last year. As a general materials science journal, Science China Materials has continued to show significant advances in this broad subject, and the contributions come from a wide range of disciplines, all with the same goal of achieving efficient, practical, and environmental friendly materials. In addition to publishing papers, Science China Materials is also active in organizing a series of academic conferences, including the Science China Materials Innovation Forum. We appreciate all the speakers for their gracious supporting of this workshop and sharing their recent breakthrough results and perspectives in their research. We are certain that their talks will surely inspire the audience with their quests for fundamental insights, their approaches in solving problems, their ways of articulating the results, and their styles of persuasive presentations. After each presentation, there will be a couple of minutes for questions from the audience. Please post your questions online, and we will select some of them for the speakers to respond. In the first session, we will have 4 speakers: Professor Stanley Whittingham from State University of New York at Binghamton, United States; Professor Donglin Ma from National Institute of Scientific Research, Montreal, Canada; Professor Hongjin Fan from Nanyang Technological University in Singapore; and Professor Nanfeng Zhang from Xiamen University in China. And welcome you all to join this workshop, and not only this morning, and will also be tomorrow. And I also want to say Professor Yadong Li, because of his other obligation, he could not come here to join us today, and that was the reason I give a welcome speech on his behalf. Thank you. And with that, we will move to the first session with our first speaker, and with Professor Stanley Whittingham. And you can see all his the introductions on the flyers, so I'm not going to repeat what has been written there, just like I've read my welcome speech. Professor Whittingham is the true first scientist opened the field of lithium-ion battery. And many of us have a job, has income, and thank for him. Otherwise, we will have no research, no job in this field. And Professor Whittingham won a Nobel Prize 2019. And I met Professor Whittingham in 2006 and of 2005 at one of MIS4 meeting in Boston. I gave my very first talk about the materials for lithium-ion battery. And it was in the late afternoon, late session. And after my talk, and one gentleman approached me and talked with me about my research, and gave me a lot of good suggestions, advices, and also give me the name for possible potential collaboration. And at the end, he gave me his name, business card. It says, Professor Stanley Whittingham. That time, I did not know who is Professor Whittingham. And so I know Professor Whittingham for 16 years, and about 5 years ago, I sat on a DOE panel for the review panel for the EFRC program. And Professor Whittingham was the director of one of those EFRC center. And when panel asks any question, Professor Whittingham would stand up and answer the questions. And at the end, he would repeat, is my answer satisfactory? Are you satisfied with my answer? So what I try to say, to convey is, Professor Whittingham is a true gentleman and a scholar. So in English, a gentleman and a scholar. This is Professor Whittingham. Let's welcome Professor Whittingham. And well, we can, Professor Whittingham, floor is yours.
Thank you. If you can unshare, I will then take over.
Yeah, we should. I stop my share, then let me see.
I still can't share.
Yeah, now you can share, I guess.
Yep. Okay. Hello, everybody. I think it's evening here in New York State and a bit of a rainy day, but warmer. And what I want to really do is describe how lithium batteries started up, how they now can help us with renewable energy and advancing green energy. But first, let me thank the folks who really supported my work over the many years, and that's US Department of Energy. They've supported me now for somewhere over 30 years. And I'm at Binghamton University, which is part of the State University of New York system. So this is what I'm going to cover today, starting in 1972. So you can see where we've come from. And I should remind any youngsters in the audience that we didn't really have things called computers back in 1972. The largest computers we had then that we as individuals could use had about 8K of memory in them. So very, very different situation than today. So I'll describe how lithium batteries have developed over that time, how they can impact a cleaner environment. I'll very briefly say what they are, just in case anybody doesn't know, then get into their limitations, and then some scientific opportunities and challenges, and then describe why we do not want any catalytic reactions. And this is one of the big challenges now that we're pushing the limits of all the materials. So let me first thank Exxon for initiating lithium rechargeable batteries. They had the initiative to invest in essentially all renewable energies, fuel cells, batteries, solar cells, nuclear reprocessing back in the 1970s. And they put quite a lot of money into looking at lithium TiS2, and this is single crystals that we used in those days. They came in various shapes and sizes, but we made two batteries that I'm showing you here. This is a paperweight that we used to give away to potential customers, has a lithium-ion battery here, a watch, and a little solar cell. And this particular one's still sitting on my desk here, and it's still working. Now it's about 45 years later. So a well-made lithium battery will last, I won't quite say forever, but close to it. Beneath that is a larger battery. It's about 6 inches by 4 inches by about an inch thick. And this was used to turn on and off a motorcycle headlamp all week long at the EV show in Chicago in 1977. So there's been lots of interest in electric vehicles for more than 50 years now. So just take a look at this. This is what we probably call a coin cell these days. You want to see one of these, you'll now have to go to Stockholm. We managed to hunt in the basements and found one of these coin cells and the little button cell, and also Exxon's marketing brochure, and these we gave as a gift to the Nobel Museum. So let's look at where we've come from these little cells here to what we have today. So this is the present situation. I'll show you just examples of a few vehicles here. This is a two-seater electric car. It was one of the first 4 or 5 electric vehicles on Bermuda in March of 2019. And tourists aren't allowed to drive cars until they brought these electric vehicles. Also, this is a small car. Next to it is 2 trucks that are north of Seattle at Packard, which owns Peterbilt. And this is a 16-wheeler. These are all the lithium-ion batteries. And this is a garbage truck, again with lithium-ion batteries. And the garbage truck is almost a perfect use of an EV. It's stop, start, up and down all day long. And I got the opportunity of driving both of these on their test track. Beneath that are 2 electric vehicles from England. The UK ambassador took to Stockholm. This is a Jaguar, and this is a London taxi. And she used this to go to and from the palace. And Britain's really pushing green energy. They will not be allowed to sell internal combustion cars after about 2030, I understand. And clearly we all know how lithium-ion batteries have been used in cell phones, computers, and so on. And really where batteries are becoming extremely important now is enabling renewable energy, whether it's the sun or the wind. And this is a wind farm in West Virginia. This is, I think, 32 gigawatt hours of battery storage. It was very large at the time that was built, but it pales by what we have today. So let's just look at what is happening with renewable energy today. And I picked an example here from Texas, not exactly known for its friendliness to climate folks, but it turns out as of last August, 94% of all the new planned generation capacity is renewable. Mostly solar, wind with a lot of storage attached to it. The big advantage of renewable, minimal staff, no fuel cost once it's operating, okay? And it's intermittent, but so it needs storage. And on the right-hand side, I show you the largest storage facility in the world now. This is about 1.5 hours south of San Francisco in Moss Landing. This is 1.2 gigawatt hours, and it started up last December. So this was a gas-powered power plant, and it was inside this building, and this building is now full of lithium-ion batteries, and it's going to expand to 1.6 gigawatt hours this year, and it's already been approved for expansion to 6 gigawatt hours in the future. So a huge use of lithium-ion batteries. Clearly, lithium-ion batteries are now cost-effective. They are making money for their investors. But let's look at where we started out. So we'll do a bit of history here. Go back to TIS2. And my apologies for these red stripes. I don't know where they came from. So we had TIS2. The big advantage of it is what we call a soft conducting lattice. In other words, it's a metallic conductor, covalent bonding. So ions can diffuse very readily in it, and you do not need to add any conductive additives, such as carbon black. And you can see on the left-hand side, the example of lithium. And this is at 10 milliamps per square centimeter. Remember that number for the moment. This is the 76 cycle. And the difference between a charge and discharge curve is just the resistive losses in the electrolyte. In the middle there is the same behavior for sodium. This is now open circuit voltages. You can see this is much more complicated. Whole series of phases formed, as opposed to lithium where it's a single phase for all compositions. And on the right-hand side is the best data available to date for a magnesium TIS or any magnesium battery. And this is with TIS2, and this is the work of Linda Nazar at Waterloo. And no one has got this many cycles in a cell, in a magnesium cell, and essentially 100% Coulombic efficiency. The challenge here, divalent ions don't diffuse very fast. So this data was collected at 60 degrees centigrade, and the current density is only 0.04 milliamps. So much, much slower than lithium. The other key feature to note here is the voltage is about 1.2 volts, so almost a volt lower than lithium. And this is why magnesium cells are not going to be commercially viable. They got a much lower voltage, much lower rate capability, and therefore much lower energy density. But we really need to understand them to better understand how diffusion occurs in these materials. And there's ongoing work on calcium, which is a bit bigger, so might diffuse somewhat better. So let's look at the history of lithium-ion batteries over this last 50 years. So we start out in 1972. Exxon was then Esso. Some of you may be old enough to remember that. We start out with a lithium anode. We very quickly learned that you've got dendrites, so we switched to lithium aluminum. That only cycles maybe 100 times. It's a very brittle compound, so it tends to crumble up. Akira Yoshino was interested in polyacetylene as an electrode, and then discovered that graphitic carbons were very good hosts. And that's what I show you right here. This is essentially graphite with lithium between the layers. The challenge with the carbon is you need 72 grams of carbon to store 7 grams of lithium. So not very effective on the weight basis, and the anode also takes up half the volume. So a lot of work now trying to switch to tin or silicon, which react with more than 4 lithium ions, but many challenges there because it expands by more than 300%. So the holy grail is still to go back to lithium, and I'll show you some data on lithium in a moment. If you look at the cathode, we started out with a layered compound lithium titanium disulfide. John Goodenough, who was then at Oxford studying the magnetic behavior of lithium cobalt oxide, noticed a similarity in structures and studied this as a battery electrode, and all the rest is history. The challenge with cobalt oxide, though, the cobalt is rare and expensive, so most of the cobalt is now replaced by nickel and manganese or by nickel and aluminum. Sometime later, John also came up with the idea of using the phosphates, in particularly lithium iron phosphate. It cycles very well, and this was really the work that Yet-Ming Chang and A123 did to commercialize John's idea, but it only has about half the energy density of the NMC. So it's interesting for some applications, but not for most mobile ones. So what we've been trying to do is try to increase the energy density of these phosphates by seeing if we can intercalate 2 lithium ions into them or 2 sodium ions into them. And I'll show you a little bit of that data in a moment. So if you look at the present status of lithium-ion batteries, in that oval in the middle, the percentage there is the percentage of the theoretical energy density on a volumetric basis that commercial cells achieve today. So between 11% and 25%. So there's still huge opportunities for improvement. And the right-hand column over here, this is on a weight basis, and you can see those are about 25%. So I'm part of a DOE consortium, the Battery 500 consortium run out of Pacific Northwest National Lab, whose goal is to get this up to 500 watt-hours per kilogram. And I'll show you a bit of data in a few minutes. So to increase that, we've got to get most of the carbon out. We've got to get more lithium into the materials. And ideally, we need fundamental research to improve the ionic and electronic conductivity. This will allow us to make thicker electrodes and therefore reduce the amount of current collector and separator. So let's just see what the challenges are. What we have here is a plot of the thermal stability versus the discharge capacity for a range of these mixed metal oxides. That's nickel, manganese, cobalt, aluminum, what we call NMCA, and the formula I give it is given at the bottom here. And you'll see the nomenclature like 622 just means 60% nickel, 20% manganese, 20% cobalt. So you'll notice on here, if we want the highest thermal stability, we have the lowest discharge capacity. If we want a high discharge capacity, then we have low thermal stability. And the thermal stability is really a measure of how reactive the materials are and therefore relate directly to capacity retention. So if you want high discharge capacity, you want very high nickel content. In this case, it's 85%. If you want high stability, we want low nickel content. This is about 1/3 nickel. Our goal is to get to this blue box, and I'll show you some of our work in a moment. So we have this challenge of energy versus safety, which really relates in the end to the challenge of reactivity. So where do we stand on this material? At the bottom there in the plot, you can see our history. So in 2017, we achieved 300 watt-hours per kilogram in a pouch cell. In 2018, we got now about 225 cycles, so we improved the cycling greatly. In 2019, we again got the same number of cycles. Now we pushed it up to 350 watt-hours per kilogram. And as of last October, we now have somewhere around about 400 cycles at 350 watt-hours per kilogram. So our goal is to still push it higher. The morphology of these materials I show you here, these are about 100 to 200 nanometer primary particle, and the secondary particles are about 5 to 20 microns across. And we use this, what we call meatball morphology, to get good packing. Here's the typical cells we make. They're about 2 ampere hours. And there's Jay Xiao at Pacific Northwest National Lab, who's responsible for making these cells. Then she sends them to Idaho National Lab for the actual testing. So on a volumetric basis, these are about 700 watt-hours per liter. So we're making very good progress, but to get to the next step of 400 or higher, we've got to do better. And one of the key things we have to do is use all the material. So if you look at this plot, you'll see as we charge it, and we'd normally go to about 4.4 volts, we get a nice curve here. But when we discharge, we do not get all the lithium back in again. In this case, I'm showing a loss of about 30 milliampere hours per gram. So you lose between 10 and 20% of the capacity on the very first cycle, and you never recover that. So our goal was to determine what limits that capacity and then come up with a solution to solve it. So what we determined pretty quickly is that lithium diffusion is the problem. It's not clear yet whether that's in the bulk of the material or just in the surface. But the solid circles here are lithium in diffusion, and the open circles are removing the lithium. And you can see there's no problem in removing the lithium until you get to the very end. So you can do fast charging with these materials with no problem, but you have difficulty getting all the lithium in. And you can think of this, if we're in normal times and you were in your lecture hall, and the lecture hall was at, say, 70% capacity, the empty seats are placed scattered around the middle of the lecture hall. So to get another person in, everybody has to move. And this is just what the lithium ions see. And what makes it worse, the lithium ions jump by a die-vacancy mechanism, so they need 2 vacancies, so it makes it even more difficult. So you can see this is dropping off by almost 4 orders of magnitude. All is not lost, and I'll show you why in a moment. So to double check diffusion was the culprit, we actually looked at the behavior of a couple of temperatures. Here is room temperature, charged to different voltages, and you can see the capacity increases. You get more and more lithium out the higher the voltage you go to. Clearly 4.2 volts is too low to be of interest. 4.4 volts, you notice the charge and discharge goes right on top of each other. But at 4.6 volts, they're starting to separate, and at 4.8 volts, they're separating even more. This is because we're now getting side reactions and resistive species on the surface. So we don't want that. And you'll notice the way we test for diffusion control, we discharge to 2.8 volts, then we hold it there for a few hours, and you can see we get more lithium back in all these cases. If we go to 45 degrees centigrade, now at 4.4 volts, you can see the first cycle loss is much less. We don't have to hold so long to get some of it back. 4.6 and 4.8 volts, the charge and discharge curves are separating even more. So we're clearly out of the stability range of the electrolytes. So we're now restricting our cycling behavior to 4.4 volts. And there are clues that we can solve this problem, because if we look at pure lithium cobalt oxide, very similar structure, it does not show a first cycle loss. So we look at the 80% nickel material, black is room temperature, red is 45, and you can see in this case we just charged it at 120. On discharge at room temperature, we now held it for 100 hours, and you can see we got all the lithium back in. So again, clearly diffusion controlled of some manner. Lithium cobalt oxide is the same at room temperature and 45 degrees centigrade. The only difference really between these, this is a single phase reaction, and the lithium cobalt oxide is a 2-phase reaction. So it's almost exactly the opposite. We'd expect problems with lithium with a 2-phase reaction, not the single phase. So our goal's been trying to make our NMCs behave more like lithium cobalt oxide. And here's what we try to do. We substitute in a lattice and coat the material. And here we're doing with a lithium niobium oxygen solution. And it doesn't matter whether we use 1%, 2%, 3%. You can see we've cut the first cycle loss by almost 50% here. And if anything, the capacity here is a little larger as well. So what happens when we do this, we coat it so it gets a coating on the outside, and this diffuses at 500 degrees, a few nanometers into the surface here. But what we found out was very interesting doing a combined exon-neutron study. Some of the niobium that goes into the lattice, in fact, displaces the manganese. So our outer layer is, in fact, a mixed niobium manganese phase. So we think we've got a clue here, and that we can push this all the way so we don't have any loss eventually. Now, that's one of the major materials of interest. I've talked about TiS2. The folks in Vancouver, Moly Energy looked at molybdenum disulfide in the 80s extensively, talked about that already. Lithium iron phosphate, I mentioned, was of interest for storage, and it was used for grid storage maybe 10 years ago. It's gone out of favor in the US at the moment. It's a one-dimensional structure, no first cycle loss. So again, a clue that we can solve it. But the energy density is really too low for any portable application. So our goal has been try to build on the thermal stability of this material. This material does not involve oxygen on charging, unlike the layered oxides. But you cannot have iron going to the 4+ oxidation state because it's too high and decomposes the electrolyte. So we've been looking at vanadium. We can go from vanadium 5 to vanadium 4 to vanadium 3. And clearly I wouldn't be talking about this unless we had been successful. And I show you two of our students, one of my students and one of Claire Gray's students in Cambridge, England, picking up the award from the Secretary of Energy in July of 2019 in Washington, D.C. So for these fairly complex systems, to make breakthroughs, you really need very much a multidisciplinary team. So we had 10 different partners on this effort, experimentalists who made good materials, characterization experts who worked on the big synchrotrons, and then a group of theorists who helped us choose the right avenue to do our experiments, and then helped us calculate what the diffusion coefficients might be. So what is this material? It's a tunnel structure. In this case, the tunnels are in all 3 directions. And what we're interested in doing is putting 2 lithiums into this lattice. And the way we made this was using a soft chemistry approach. So we dissolve all our reactants into a solution, in this case 95% ethanol. You need about 5% water to stop over reduction of the vanadium. Then you just heat it up for 1 to 3 days at about 180 degrees centigrade. Then we get this nice structure. It's full now of protons, and we want lithium. So what we can do here is gently heat it, and we can drive all the protons out, and we do this in oxygen. We can also pull the protons out in an electrochemical cell. So now we've got the empty lattice, and we really want to know what the structures of these materials are. So we use a technique originally developed at Exxon, which is a chemical approach, not an electrochemical approach to make the products. Because in an electrochemical cell, you've got binders, you've got carbon black, and so on, and that complicates the measurements. So at Exxon, we developed the use of butyl lithium. The only byproduct for this is normally octane or butane and other materials. So the clean, easy materials you can get rid of. And doing that, we were able to work out the structure of this material and of some of the other ordered materials. But probably most important is we found out when we put lithium into this material, the lattice only expanded by 8.5%. That's in fact less than what graphite expands, which gave us a clue that we could have a stable structure here that might allow us to put lithium in and out many, many times. So what does this material look like? They're little cuboids, about 100 to 200 nanometers in size, extremely uniform. What we do is, because this is a phosphate and therefore a very good electronic insulator, we have to make it a conductor. So we mix this with graphene. It's much more effective than carbon black. And you can see the electrochemistry on the right-hand side here. So we have a flat plateau here, vanadium 5 to vanadium 4, then here vanadium 4 to vanadium 3. And you can see a series of bumps here. This is as the lithium is tending to order in the lattice. But the key thing to note here, the black curves is the first cycle, the purple curves are the 50th cycle. It's in fact better on the 50th cycle than the first cycle. So we got proof of concept that we can intercalate 2 lithium ions into a lattice without destroying that lattice. And we've done the same thing for sodium. So we now know we can do that. All is not over with, there was still a number of challenges. If we look at the kinetics for these 2 reactions, they're very, very different for the high voltage plateau and a low voltage plateau. So in the high voltage plateau, it's a two-phase reaction, VOPO4 to LiVOPO4. And you can see as we increase the rate, this is the black one is the slowest rate, increase the rate, we're losing capacity. And we plot it again on the right-hand side the same way. So at a 50-hour rate, we get about 130 to 140 milliamp hours per gram. When we go to the C rate, that's 1 hour rate, we're down to about 30 or 35. So a big drop, big hindrance, but we believe we can solve this by substituting in the lattice, just like we did for lithium iron phosphate. Pure bulk lithium iron phosphate is not a good cathode. You have to either nanosize it and or substitute other elements such as vanadium or magnesium to make it work. In total contrast, however, in the low voltage regime, that's the regime down here, to study that, we first put one lithium in, then we put the second lithium in, then just cycle backwards and forwards for the second lithium. And you can see in contrast to the 4-volt one where we lost capacity as we increase the rate, here there's essentially no change in capacity whatsoever. There's a bit of a difference here due to the resistance of the electrolyte. So this is an exceptionally high rate, but there are challenges. So here is the discharge capacity in red. So very, very stable, independent almost of the rate. In the black is the charging capacity, and you can see that the charging capacity is quite a lot higher if we're at the slower rate. So we're getting serious side reactions occurring here. And this should be no surprise because vanadium phosphate is used as an oxidation catalyst. So we'd expect it to react. And in fact, if we heat up our vanadium phosphate with the electrolyte, we will form H2VOPO4. So we'll actually abstract hydrogen into the material. So we have to find electrolytes where this isn't a problem. So that's one challenge. The other challenge is obviously to increase the rate capability of the higher plateau. So on my last slide, let me just show you some conclusions on what's next. And what's going to happen for batteries in the next 10 years is no different than today. These layered oxides are going to be dominant. You're going to see essentially all, if not all, the cobalt going away. Cobalt's expensive and a big child labor issue there. The phosphates were active. Lithium iron phosphate 10 years ago is now increasing in activity, particularly in China. It was very active there, then essentially disappeared because of incentives to work on the oxides. It's now coming back, and Tesla is going to use it in its lowest cost cars. What we really need for all these materials, and particularly for these vanadium phosphates, are safe and stable electrolytes. So the question people are asking is, can solid-state systems give the required power density? And the answer is yes. Here is a Mercedes bus. Towards the end of this year, this bus will be available with all solid-state batteries in it. Lithium anode, polyethylene oxide, electrolyte, and LiFePO4 cathode. And it, uses pure lithium, so lithium metal is viable for extended cycling. I should say our work at Pacific Northwest National Lab also uses lithium metal. It operates at 70 degrees centigrade, which means it probably will not be used in personal cars for a while. But the folks at Blue Solutions who make these batteries in France are claiming they will have it available for cars in 2 or 3 years. At Pacific Northwest National Lab, we're also showing excellent progress for using pure lithium metal with liquid electrolytes. So we think we can solve the problems there. The other areas where research is needed, we really need new manufacturing technologies. we got to reduce the present 60 to 80 kilowatt hours, which is used to produce 1 kilowatt hour of lithium-ion batteries, which means we got to have better mining procedures. We got to have a supply chains that are within a single continent. Whereas North America needs their supply chain just as Europe is building theirs. We cannot ship materials around the world 3 times, which is what's happening today. We also need clean recycling technologies, give us a sustainable society, and I think you're going to see a lot more activity in recycling, particularly as more and more of the large batteries from Tesla and others become available. And I anticipate that in major city centers in 10 years from now, only all electric vehicles will be allowed. They'll be much cleaner and there'll be a big incentive there. And we're all looking for President Biden here to introduce far more electric vehicles, for example, in the postal fleet and other delivery areas. So I will stop there and try to answer any questions that you might have. Thank you very much.
Oh, Dr. Chow, you're muted if you're trying to speak.
Okay, thank you, Professor Whittingham. And now it is the time for questions. Any questions? I think Professor Whittingham, and you showed those lithium, vanadium phosphate with 2 lithium ion discharge, and compare with vanadium pentoxide. You also can get the similar type of capacity. And what is the benefit to use phosphate compared with simple oxide?
The challenge with using, certainly with vanadium pentoxide, lithium and vanadium are the same size. So they become randomized in the lattice. So your voltage, I think, goes all the way from like 3.5 volts down to 1 volt. So the voltage behavior is more like a supercap than a battery.
Right.
Clearly, many years ago, there's a lot of interest in, I think, V6013, but its capacity is quite a bit lower. Mm-hmm. So the number of the phosphates have been looked at, like Li3, V2, PO4 3 times. So I think people are going to look at the phosphates more. They can look at vanadium more. Most people don't realize, I think, vanadium's the 4th most abundant transition metal, much more abundant than nickel, cobalt, or copper. Mm-hmm. And you can get it almost free from some heavy oil refineries.
Right. Yeah.
Correct. May I ask a question?
Yes.
Aston, very inspirational talk as usual. Everyone is working on cathode materials, electrolytes, solid electrolytes, and anodes. I am wondering whether you feel room for increasing energy and power density by improving passive materials. Is there room for improving design with current collectors, separators, packaging, making thicker electrodes, and so on?
Thank you very much, Joey. The answer is definitely yes. We want to eliminate as much as we can of what we call the dead weight. Mm-hmm. So there's a lot of interest in trying to get rid of the copper current collector because that's heavy. We would like to make all the electrodes thicker, but we've got to have the ions moving faster to do that. And then the issue is, can we build 3-dimensional systems that would improve the energy density? Mm-hmm. So I think there's a lot of effort at optimizing the design of the battery, and that's where a lot of the effort has come from. But one has to be very careful. There was a big issue, was it 20, 30 years ago with the solid polymer batteries when they were made by Avastor in Canada. They made the electrolyte too thin, So the dendrites grew right through the polymer, and I think AT&T had installed maybe half a dozen of these, and they all caught fire within a month. So one has to be very careful. And I think there's interest now in having a kind of combo electrolyte where it's polymeric but has a ceramic coating on it. So it will be more stable. But anything we can do to make the electrodes much thicker will immediately improve the energy density.
Thank you.
Great. Any more questions from audience? If not, let's thank Professor Whittingham again, and thank you. And we are just moving to the second speaker, and Professor Dongling Ma. And Dongling, if you look at her picture or face, she's still so young. And
No.
Yeah. Normally, I always thought that the chair professor is for aged people. And so Dongling already got a chair, or Professor Ma got a Canadian research chair. And well, I also have something to tell about Dongling. And you know, I always love beautiful ladies, but Dongling made me remember her name by complaining to my face, say, look, he forgot my name again. And then that was the time I remember her name. And so I don't know how many times I forgot her name. Let's welcome Dongling Ma, and for now it's your floor.
Okay. Thank you, Professor Cao, for very interesting introduction. Also, good evening or good morning, you know, everyone, for your presence here. Here in Canada, in Quebec, we are at like a nighttime, like a nice around 9:30. So today, I'm very pleased to share with you our recent work on nanohybrids. Let me show laser pointer. Can you see laser pointer?
Yes.
Yes.
Okay. So as Professor Cao introduced, I'm professor at INRS Canada. So my group basically has started to work with different functional nanoscale materials for energy, environmental, and biomedical applications. For example, we have worked with nanoparticle catalyst, near-infrared quantum dots, plasmonic nanoparticles of different shapes. But for the past decades, we shift our research interest more towards nanohybrids. We have two good reasons for that. The first reason is to get improved performance and properties, as demonstrated in some of our work, like plasma-enhanced photovoltaics, plasma-enhanced photocatalyst. The second reason to work with nanohybrids is to get multifunctions. For example, in this case, we combine luminescent materials with magnetic materials. So in a single nano architecture, so these nanoparticles, they can emit photons used for photoluminescence imaging, and also can be magnetically confined and used for magnetic resonance imaging also. So these particles, they are multifunctional, and they can't be achieved with a single material. So today's talk, I would like to give you several examples to highlight the important application of nanohybrids in energy, environmental, and biomedical applications. First, I would like to talk energy. I think Professor Whittingham have already given a very nice introduction about the importance of energy. As a human being, to live, we need energy, and our demanding for energy is ever increasing. There are two reasons, at least. For example, if you look at this figure, it shows that for almost every major technology advancement, there's a dramatic increase in energy demands, in energy consumption. And the second reason is due to increased population. 2019, we are at 7.7 billion. It's predicted that to 2040, we will have more than 9 billion people on the Earth. So due to the technology advancement and also increased population to meet our current lifestyle, we need more energy to survive. It has been predicted that by 2040, we need twice as much energy as it produces today if we can't improve energy efficiency. But related with increased energy consumption, there are some serious problems such as environmental pollution, greenhouse gas emission, climate change. They all impose dangerous threat to us human beings. So what's the reason? The reason is that our current energy structure has certain problems. If you look at global energy consumption in 2019, you can see over 95% of energy we consumed came from oil, coal, and natural gas. Only slightly above 10% of energy we consumed came from hydroelectricity, nuclear power, and renewable energy resources. Related with the use of these fossil fuels, there is a large increase of CO2 emission. And also we know sooner or later, these fossil fuels will be used up. So it's very important to develop new energy resources which are clean, renewable, and sustainable. We're living in Quebec, Canada. Here we use a lot of hydroelectricity, and also as a professor, Wintingham mentioned, in Texas, there are a lot of renewable energy resources. But globally, if we look at these renewable energy resources, solar energy appears most attractive. It strikes the Earth at the energy level of 120,000 terawatts. This energy from the solar system, like per hour, is higher than the whole world energy use per year. So you can imagine if we can make good use of this solar energy, we shouldn't have much trouble in meeting our urgent energy demands, yet without any negative impact to our environment and climate. So there are different ways to use solar energy. For example, it can be transformed to electricity by solar cells, to thermal energy, or to chemical energy, which can be easily stored and transported. For example, by water splitting, we can get a clean fuel of hydrogen. By CO2 reduction, we can get CO, which is an important component of syngas, which can be used to synthesize many useful organic materials. And also solar energy can be used to photocatalytically degrade pollutants in our environment. So in this case, even better, we use clean energy, solar energy, to help with a better environment. So the overall picture sounds beautiful, but unfortunately, many of these processes are not still very efficient yet. So let's look at the solar photo processes. Basically, semiconductor materials absorb solar photons to generate electrons and holes. These electrons and holes can be used in redox reactions for photocatalysis. Of course, they can also recombine. In this case, they don't contribute. They are not very useful for photocatalysis in this process. So to make a solar photo process more efficient, photocatalytic materials need to absorb as much sunlight as possible, need to have efficient generation of charge carriers, have surprise charge recombination, and also have efficient surface reactions. Unfortunately, at this moment, most of photocatalysts, they are only able to absorb UV photons. Some are able to absorb like a short wavelength part of visible photons. But if you look at the solar spectrum, it's very broad, ranging from UV up to over 2000 nanometer in the near infrared. So for photocatalysis at the current stage, a lot of photons in the near infrared, they are wasted, they are not used. And the same is true for the long side, long wavelength side of visible photons. So we think if we can increase solar photon harvest, we should be able to increase solar photo process efficiency. Of course, photocatalytic materials also need to meet other criteria. So there are different strategies to increase solar photoprocess efficiency, such as junction formation, doping, defect engineering, coupling with plasmonic nanoparticles. So I will not go over all the strategies due to time limitation, but I will give you a few examples. So the first part, I will talk about the nanohybrids for energy and environments. I would like to show how the nanohybrid can help with the performance and behavior of photocatalysis. So to increase solar photon absorption and to get broadband photocatalytic behavior, we have worked with plasmonic semiconductor nanohybrids. So in these cases, we combine plasmonic materials with the different semiconductors in different configurations. And in this latter case, we also combine the platinum and gold. In this case, we use both plasmonic effect and synergistic alloying effect of platinum and gold for photocatalysis. So in all these cases, we observed the increase of light absorption and also increased broadband photocatalysis. But you can see that these systems involve expensive gold and platinum metals, and for the long run, they are not very sustainable. So that's the reason that why we started to look into cost-effective two-dimensional materials like black phosphorus. So this student did a nice work. He combined black phosphorus with the C34 to make a 2D on 2D nanohybrid assembly and to get broadband photocatalysis behavior. So black phosphorus has a layered structure similar to graphene, but unlike graphene, it has a zero band gap. It shows direct band gap tunable from 0.3 to about 2 electronvolts, depending on the number of layers. And it has a wide working spectral range from visible to near infrared, and also relatively high carrier mobility. So all this predict that BP can be very interesting photocatalyst. But before we can use them, we need to overcome some challenges. For 2D BP nanosheets, the synthesis is kind of difficult. I mean, for large scale, high yield synthesis is kind of difficult. So this brilliant student developed a new method. We call it NMPS assisted synthesis of BP nanosheets, and the work is currently patent pending. So in this synthesis, what he did is that he introduced tiny NMP nanocrystals into BP structure to decrease the interaction between BP sheets to help exfoliation of BP nanosheets. The advantage of this method is obvious. For example, we have much higher yield, 75%, with respect to normally reported 15 to 30% of yield, and energy requirement is significantly low, and the duration time is also much shorter, less than 2 hours, as compared to normally reported 8 to 20 hours. And from this synthesis, we can get BP nanosheets with atomic layers, about 6 layers. Over 90% of BP nanosheets have thickness around less than 10 nanometer, and also colloidally, they are very stable. No aggregation was observed over 4 weeks during the storage. But how about the chemical stability of BP? This is the second challenge we need to address, because BP is known chemically unstable. It can be easily oxidized by air, humidity, moisture. So we studied chemical stability. We proposed a strategy. We stack BP on the surface of C34. So basically here is either mapping shows like a C34 and a BP stacking structure. We stack them together to increase the stability of BP. So here you can see that under visible light, longer than 420 nanometer irradiation for 24 hours. For pure BP, initially it doesn't have any P1 peak. This is related to the oxidized black phosphorus. So initially there's no peak, but after 24 hours under irradiation, we observed a dramatic increase of P1 peak. But in clear contrast, for the nanohybrids after 24 hours, we only see minimal increase in this peak. So it indicates the chemical stability of BP is largely increased due to this 2D on 2D approach. So then we would like to try them for photocatalysis. The reason we combine BP with C3N4, one is for the stability of BP, but the other is because C3N4 is a very promising visible response photocatalyst. But C3N4 still has very limited absorption, only up to about 460, 470 nanometer. So we hope by combining BP with C3N4, we can increase absorption. And here, theoretical calculations done by our collaborator, you can see that for 6-layer BP sheets, absorption basically can be extended into near-infrared and the long side part of visible range. And these calculations are quite consistent with our experimental results. You can see BP can absorb up to the near-infrared range. So we combine BP with the C3N4 for the nanohybrid. We get improved light absorption. And with that, and the solar simulator irradiation, you can see photocurrent largely enhanced as compared to plain C3N4. So under visible light irradiation, the hydrogen evolution is largely increased. For 3% of BP on C3N4, hydrogen generation rate is about several times higher than that of BP and that of C3N4. Because in this system, BP only accounts for 3%. So basically, most photons are absorbed by C3N4. And this increase can be easily explained by this energy level diagram. So we measured energy levels, and you can see C3N4 and BP basically form type 1 junction. And the C3N4 mainly absorb photons to generate electrons holes. Electrons can be injected into BP used for photocatalysis, and holes can be directly captured by scavengers. So in this case, hydrogen generation is largely enhanced. And the charge transfer from C3N4 to BP was also confirmed by decrease of photoluminescence intensity and also the shortening of photoluminescence lifetime of C3N4. So we confirmed that by combining C3N4 with BP, we show largely enhanced visible activity. But how about longer wavelength activity? Remember, one reason we want to combine BP with C3N4 is to extend light absorption. So we tested photocatalytic behavior longer than 475 nanometer irradiation. At this irradiation, basically, C3N4 doesn't absorb, only BP absorb. And for this longer wavelength irradiation, we also observed a large increase of hydrogen generation as compared to pure BP and pure C3N4. Actually, pure BP and pure C3N4, they don't show any activity under this longer wavelength irradiation. At the first sight, maybe it's difficult to understand because BP and C3N4, they form type 1 junction. How come electrons and holes excited by photons can be jumped to C3N4 to have efficient charge separation? How come they don't quickly recombine? So to answer this question, we did chemical characterizations. We found that at the interface between BP and C3N4, they form kind of interfacial bonding between nitrogen and phosphorus. And these interfacial states serve as a charge separation site to enhance the charge separation. And basically, electrons can go to this shallow trap site to suppress the charge recombination, and the electron holes can be used for photocatalysis. So with this example, I show that by combining BP and C34, we can extend absorption, we can enhance the charge separation, and get broadband photocatalysis. In the next example, I would like to show that a homojunction can also help with broadband photocatalysis. So by definition, a homojunction is a semiconductor interface that occurs between layers of similar semiconductor materials. The most famous example is the P25 titanium nanoparticles, which has been used quite a lot as a photocatalytic benchmark. P25 basically has two phases of titanium nanoparticles, rutile and anatides, and the catalytic activity is much higher than pure rutile and pure anatides nanoparticles. It's because these two phases, they form kind of like a type 2 junction, which can help with charge separation, suppress charge recombination, and thereby help with photocatalysis. So in this example, I would like to show that we can form MOF homojunction, which can lead to broadband photocatalysis. So this work was done by my previous postdoc, Yannan Liu, and now he's doing his second postdoc in Germany. And here I would like to show homojunction help with the CO2 reduction. So about the synthesis first, we use a hollow gold silver nanocubes as inducers to induce the formation, the interaction between cobalt precursors and the TCPP to get a cobalt MOF structure. And the small plate was formed first, which induced further the large plate, the synthesis, to have nanosteps, which composed a smaller nanoplate of cobalt MOF and a larger cobalt MOF. And we have used the synchrotron techniques and other techniques to confirm the formation of cobalt coordination with the nitrogen or with oxygen. So about the sizes, we use EFM to characterize, and here shows a typical MOF nanostack structure. The top nanoplate has a dimension about 0.75 micrometer in the lateral size, and the thickness around 130 nanometer. And for the bottom nanoplates, the lateral size is about 1.7 micrometer, and the thickness is about 174 nanometer. And interestingly, we also observed some nanoplates. Looks like the top plate is mixing, and here we can see a little bit dent about 27 nanometer. So we think this was caused by the missing of the top plate for whatever reasons. So here shows that looks like top nanoplate is partially embedded into the bottom large plate, so the interface bonding can be quite strong. We then characterize the chemical composition by doing EDAX mapping. Basically, we did EDAX mapping for this nanostack and for the top and the bottom or the edge plates. Basically, we can see they all contain carbon, cobalt, oxygen, nitrogen. And from other chemical characterizations, we don't see any gold and silver detectable, in this nanostack structure, although we use gold and silver as inducers. But we have looked at the EDAX spectrum data very carefully and characterized the cobalt concentrations. And we notice, like in the center part, there are more cobalt as compared to the edge part. So it means it looks like the top plate has more cobalt concentration as compared to the bottom nanoplates. Then we characterize the crystal structure of this MOF nanostack. We first did electron diffraction on the edge part. Then we can observe one side of diffraction spots. And then we did electron diffraction on the center part. Then we can see two sets of diffraction spots. We think this indicates that the top plate and the bottom plates, they have slightly different crystal structure. And we observe the similar thing by high resolution TM. So here is the center part, here is the edge part. Then we observe slightly different lattice fringes. So we think that the interplanar distance of the top and bottom nanoplate differ slightly, but both have a tetragonal crystal structure. Then anyway, we did more experimental work and also did theoretical calculations and finally identified the structure. The top plate has lattice constant of 1.43 and the bottom plate has slightly larger lattice constant of 1.64. And the slight difference from the top plate and the bottom nanoplate also confirmed by low loss electron energy loss spectroscopy. So we did a low energy loss mapping, and we can see in between 20 to 35, there's slightly intensity difference. And then if we look at Borg plasma peak, you can see the top plate and the bottom plate, they have a slightly shifted peak position. This indicate that top plate and the nanoplate bottom plate, they have a slightly valence electron density difference. So based on all these characterizations, we can see the bottom and the top nanoplates differ slightly. Because of that, they also show quite a different band gap structure and different energy levels. This basically abated from our experimental data and also confirmed by theoretical calculations. So we think with this type 2 structure, we should get extended absorption and also get efficient charge separation between top and bottom nanoplates. So I will not enter into details, but we visualized the charge transfer between top and the bottom plates by using in situ surface voltage photovoltaic microscope. So basically, we measured contact potential difference with AFM in the dark and also under illumination of 400 nanometer, 20 nanometer LED at different intensities. And then we plot the contact potential difference for the center part and for the edge part. Then we can see surface photovoltaic is much higher in the center part. So it indicates that the top nanoplate can accept a photon electrons transferred from the bottom nanoplate. So by using this technique, we confirmed charge transfer from the from the bottom plate to the top plate, means from larger nanoplate to the smaller nanoplate. So this is consistent with our optical data. So because of that, absorption is broadened, charge separation is enhanced, photocatalytic activity is increased by about 2.5 times as compared to single MOF nanoplate. And also this hybrid show very high selectivity for CO. Basically, no hydrogen was detected, only CO is detected. So we are quite happy with these results. So using this example, I show that by forming hybrids of MOF homojunction, photocatalytic activity can be largely enhanced. So with that, I think I can finish the first part. Now I would like to quickly go through the second part, how nanohybrids can help with biomedical applications. So health issues have been listed as the top 10 global challenges facing humanity. I don't think I need to mention too much, especially now we are in the global pandemic of COVID-19. It's very important to detect the disease in the early stage and also have effective treatment. And the nanohybrids, which can combine photoluminescent materials and superparamagnetic materials, can be a promising solution to solve many health issues. So due to time limitation, I will not enter into details, but I would like to quickly give you some information about the superparamagnetic particles. Basically, they combine advantages of ferromagnetic materials and paramagnetic materials. Same as ferromagnetic materials, superparamagnetic particles, they can show high saturation magnetization. It means they can can be easily magnetically confined. On the other hand, same as paramagnetic particles, they can show zero coercivity and remnants. So it means that they can quickly respond to magnetic field and they can be easily redispersed without forming any permanent agglomerations. So with these superparamagnetic properties, superparamagnetic nanoparticles can find many useful applications in biomedical field, such as hypothermia, drug delivery, magnetic resonance imaging, and the separation and confinement of trace amount of biospecies for detection. On the other hand, luminescence can be also very interesting for biomedical applications. In this regard, quantum dots are very promising. As compared to traditional dye molecules, quantum dots, they show higher signal intensity and better photostability. So they will allow more sensitive photoluminescence detection of any biospecies. And from this figure, you can see that for bioimaging, there are two wavelength ranges. Basically, skin, fat, and blood, they can absorb less and also scatter less. It means if we do bioimaging in these two biological windows, we can have a higher signal-to-noise ratio, and therefore we can get a deep tissue imaging. So interestingly, for quantum dots, they can be easily tuned to emit in the near-infrared range in these biological windows, which have been very difficult to achieve with traditional dye molecules. So NAME's group has done careful studies, theoretical and experimental studies, identified these two biological windows beneficial for in vivo deep tissue imaging from 700 to 950 nanometer, from 1000 to 1350 nanometer. And beautifully demonstrated by Kim's group in his pioneering work in 2004. They used near-infrared emitting quantum dots, I think, in the first biological window, and for photoluminescence image, which can be used to guide the surgery in small animals. So because of that, we would like to work with near-infrared quantum dots, but we want to work with quantum dots which can emit in the near-infrared, but also can be excited by near-infrared light. Then we combine those near-infrared quantum dots with superparamagnetic iron oxide nanoparticles in different configurations for different biomedical applications. So here I will only give you one example. In this case, we combine multiple magnetic particles and multiple quantum dots into single nano architecture. So for near-infrared quantum dots, we developed microwave-assisted approach for large-scale high-yield synthesis. We started with light sulfide quantum dots, then we put cadmium sulfide shell by microwave approach, and this shell can help increase photoluminescence properties and also stability, and quantum dots can be well dispersed in an organic phase. To make quantum dots water-soluble or water-dispersible, we did another coating, zinc sulfide, on the surface by microwave approach, and in the same process, we replace hydrophobic ligands with hydrophilic ligands, which allow us to transfer quantum dots into the water phase. So with this cow-shell or cow-shell approach, we get quantum dots which can be excited by near-infrared light emitted in the near-infrared and also have a high stability, high photoluminescence intensity. So here shows that we can use these quantum dots to follow the distribution of quantum dots inside the mice. And we did the deep tissue imaging. We can find quantum dots in microchannels. We put like a chicken tissue on the top of different thickness, and we use near-infrared light to excite quantum dots, and then we measure infrared emission with the camera. Then we plot the photoluminescence intensity as a tissue thickness. Then we found that for quantum dots emitting around 1270 nanometer, we can get a deepest penetration over 1 centimeter, which is deeper as compared to quantum dots emitting around 950 and quantum dots emitting at longer wavelengths, about 1450 nanometer. And also quantum dots are very stable. Here shows like after 14 months, size no change in PBS buffer, and for near-infrared imaging, 13 months, basically near-infrared intensity doesn't change. This image was captured by near-infrared camera. And then this excellent student combined quantum dots with superparamagnetic iron oxide particles, quantum dots about 5 nanometer, iron oxide nanoparticles about 10 nanometer. We used a self-assembly approach. Due to limitation, I will not enter into the details, but we can get uniform multifunctional nanoparticles in each particle. There are many quantum dots, many superparamagnetic particles, and from index mapping, we can see iron, light, sulfide, oxygen are uniform distributed in these single nanoparticles. By the way, these assembled particles about 60 nanometer in diameter. And then we did near-infrared imaging studies. We use 800 nanometer laser. We put our multifunctional nanoparticles in solution and put tissue here, and then use the camera to capture the signal. And here you can see that we can pick up a signal even about 1 centimeter in depth. And as a contrast, for quantum dots emitting in the first biological window, you can see that at the depth of at the thickness of tissue, about 4 milliliter, photoluminescence signal already decayed to 20%. So clearly, we can see the advantage of these quantum dots emitting in the second biological window for photoluminescence imaging. We also used those multifunctional nanoparticles for magnetic resonance imaging, but due to time limitation, I will skip that part. I will talk about another functionality, thermal effect. So here shows the setup. We use 787 nanometer laser, near-infrared laser, and also we use a coil to generate magnetic field. And then we can put our quantum dots sample, multifunctional nanoparticle sample into the coil. We can give the laser, or we can give a magnetic field, or we can apply both. So we put a pork tissue inside the coil. We inject multifunctional nanoparticles about 2 millimeter under the skin. And then we observe temperature increase. And we can see with the laser applied, temperature increase, with the magnetic field applied, temperature further increase. If we combine both, and the temperature quickly increase to about 45 degrees in a few minutes. As a contrast, for the part without injection of multifunctional particles, we don't see any temperature increase. So here, this study shows that by combining magnetic materials and luminescent material together, we can realize magnetothermal and photothermal effect. The advantage is very interesting because for magnetic hemotherapy therapy, usually it requires a high concentration of ion, and several orders of magnitude higher than the concentration used for magnetic resonance imaging. In our case, the thermal energy transfer efficiency is amplified 7-fold compared with magnetic heating alone. So because of that, we can use a lower concentration of iron oxide particles, so to make them also suitable for magnetic resonance imaging. And also photothermal therapy has its own advantages like easy operation, non-invasiveness, high specificity, and reasonable penetration. So with that, I think I can finish. Basically, here I show nanohybrids can be used to make multifunctional nanoparticles, which are difficult to achieve with any single nanomaterial. So here I can go to conclusions. Hybrids can help improve properties and performance and to lead multifunctions. Rational design of nanocomposite structure is highly desired for taking advantage of respective benefit. For example, due to time limitation, I didn't explain in detail, like for nanohybrids for biomedical applications. Like in this structure, we have multiple nanoparticles, quantum dots, and ion oxide particles. But we have to modify their ratio in order to get a balanced photoluminescence and magnetic properties. So the rational design is very important. And also, if we want to be metal-free, black phosphorus has a high potential in broadband photocatalysis, and a combination luminescent superparamagnetic nanomaterials lead to various biomedical applications like deep tissue imaging, magnetic confinement, magnetic resonance imaging, photothermal treatment, drug delivery. This part I didn't mention, but basically we can also use magnetic particles and different stimuli to release drugs in a controlled manner. So with that, I would like to thank our collaborators, external and internal collaborators. I also would like to thank students and postdocs who are directly involved in the work I presented today. Without their hard work, I don't think it's possible to make today's presentation. Also, I would like to thank the funding agencies from Canada federal government and Quebec provincial government. With that, I think I can finish. I would like to thank again for your attention. I'm ready to answer your questions.
Thank you, Dongming. And this is the time for questions. Any questions from the audience? At least I do have one question. Let me see. It's when you talk about the homojunction of MOF, you show that there is a difference in absorption spectrum and lattice constant, everything there. But you don't see the composition differences.
Okay, let me maybe quickly go to, I don't know why now it looks like a frozen, doesn't work. Okay, so actually, let's say this, the composition is slightly different. You know, they all like a top plate and a nano plate, they all contain like a carbon, nitrogen, cobalt, they all contain that. But what we did is that we plot the cobalt versus, other element, the ratio. And then we found that for the center part, the ratio is higher as compared to the edge part. The edge part is composed, of a bottom nanoplate, but the center part is composed of top plate and the bottom plate together, right? So because the center part shows slightly higher cobalt concentration, so we think there's a slight difference. The cobalt concentration seems higher in the top nanoplates. But it's kind of difficult to do such a characterization. So we need to run many, samples, because we need to really focus on individual nanostack instead of bulk samples. And then it's harder to differentiate the top plate and the bottom nanoplate.
Right.
Yeah.
Any questions from audience? Oh, Queenie. What was the question from audience? How the BP? Oh,
yeah, the final word. Yeah.
Yeah. Do you see the question?
Hello.
I should go to chat.
Yeah. Here the question.
In my chat, I didn't see any question.
Okay.
Yeah.
May I have a question?
Carbon nitride combine, like which way, or the mechanisms?
BP and C34, right?
Yeah.
Yeah. Okay. So for in this case, we think it's mainly like electrostatic, as a driving force for their combination. But once they combine, looks like they also have like a partial charge transfer to form interfacial states. So we did zeta potential measurements, and we can see that C34 BP, they have operate charge states, one negative charge, one positive charge at the pH value where we did the coupling. So this serves as a driving force for their coupling. But once they combined from XPS, we noticed the phosphorus peak slightly shift. And we think it's because of a partial charge transfer due to the bonding between nitrogen and phosphorus.
So I saw that somebody was having questions, or that was the question already.
Yeah, could you hear me?
Yeah, yes. I can. Yeah.
Yeah. Thank you for your wonderful talk, Dr. Ma. I'm Li Renlan, and I have a small question about the Black Forest and C3M4 hybrids. I found that for comparison, there's different percentage of BP in the hybrids, and the performance in hydrogen evolution rate is different. And my question is, what triggers this difference, and how BP percentage influence the final result?
Okay, so for this, it's really depending, on several factors, I would like to say, because, for the photocatalytic behavior, it depends on the light absorption. So it means when you use the different wavelengths, the absorbing components can be different, right? So this can contribute to photocatalysis, and also the charge transfer, the way it's transferred. So for example, when we use like a longer than 420 nanometer excitation, and in that case, we can have 3% of BP and 97% of C3M4, and the C3M4 absorb up to about 460, 470 nanometer. So in this case, because we have 97% of C3M4, you can imagine in this system, C3M4 contribute more than BP to the photon absorption, right? And in this case, because and also you look at energy levels, so the electrons excited in C3M4 can be transferred to BP and used for photocatalysis. So this is the basic mechanism for longer than 420 nanometer excitation. But for the longer wavelengths, longer than 475 nanometer excitation, in this case, even though we still have C3M4 as major components, but they don't absorb. C3M4 nanosheets, they absorb up to 460, 470. So 475, they don't absorb. So BP becomes the major absorbing components. So in this case, the charge transfer pathways are different because BP absorb photons, they generate electrons holes, and electrons can be transferred to the interfacial state due to the formation of nitrogen phosphorus bond.
Okay, thank you.
Yeah, so you basically you can see, we really have to think about, exactly what we are looking for, in order to design this, structure, because absorption and charge transfer pathways can be different. Yeah.
Okay, thank you.
Thank you for your question.
Yeah. Thank Professor Ma for such a wonderful, excellent talk. Thank you. And
thank you very much for inviting me, Professor Cao.
Thank you.
Thank you.
Let's move to the next speaker. And next speaker will be Professor Hongjing Fang. And he is much younger than me. And so we move to the younger generation. And Professor Fang is from Singapore. Is Nanyang Technological University. And the first time we met in Singapore, actually, he invited me along with other 10 or 12 professors. And today,
many years ago, I see that.
To have a durian flute. And we all had a great time there. We ate a lot of those very stinky fruits. But at the end, then we find we were totally discriminated. We could not get a taxi at all. And we struggled quite a bit. Finally, we got 2 taxis. And then I think Professor
Zhongli
Wang and some other guys, they have to walk back to their hotel rooms. And no taxi to take them back. And that was the...
You'll come again, I'll drive for you.
What?
If you come again, I'll drive for you. Now, no need taxi.
Well, let's welcome Professor Fang and for his talk. Welcome. Yeah. Now, floor is yours.
Okay, thank you very much, Professor Cao Guozong, and also thank the three chairs for inviting me. I see a lot of big names here. It's really my great honor. And how can I make my screen? Okay, so my talk is more about aqueous zinc-ion batteries. You can see my screen, right?
Yes.
Okay, I have 3 screens here, so sometimes get confused. So I will talk a little bit about the aqueous zinc batteries and some promise and some ambiguities. Means that a lot of confusions here. A lot of guys come to this area because of they think there's a lot of potentials to replace lithium battery in the future in terms of the safeties. May not be completely replaced, but it's kind of alternative technology for some application that requires high safeties. Okay, and so our group focused a lot of array electrodes for so-called high rate charge storage in the past, and so for this application, we grow active materials mainly on the 3-dimensional current collectors in order to achieve the high rate performance and in order to enable the nanostructures, enable the and also the pseudo-capacitive performances effect. Okay, so we including sodium batteries and quasi-solid-state zinc-ion batteries as well as sodium-ion hybrid capacitors work a lot on this, because if the materials is a kind of a hybrid between batteries and pseudo-capacitors, then you're making hybrid devices basically. Okay, and we'll a small part of my group also working on electric catalysts for water splittings and for other carbon dioxide reduction processes. For example, we have a series of work trying to tune the local charge transfer processes by doping engineering. Okay, and also use a conductive MOF or MOF derivatives as either as a host or as a directive material for the catalysts. And so the hot topic now is a single atom catalyst, either single metal, elemental metal, or is a metal alloy as a OR catalyst. So we're also working on this. A few papers ongoing on this work for zinc-ion batteries. Okay, so all these catalysts for either alkaline water splittings as well as the zinc-ion batteries. So there's for the new batteries, and so this diagram is taken from my previous postdoc Dongnan Shao, who is now a full professor in Fudan. So he has published a few review articles on this aqueous batteries, try to promote aqueous batteries. So in addition to most popular metal ions, we also have non-metal ions. Okay, for example, the alkaline ions, fluorine ions, chlorine ions, and even protons and ammonia ions. All this positive non-metal ions can also be, or all this non-metal ions can also be used for battery carriers, as has been demonstrated. And for zinc ions, actually, the ionic weight is highest compared to other metal ions, but in terms of the cation radius, actually is rather small. It's not much bigger than the lithiums. Okay, and the hydrated ions is to be a challenge compared to others. Is also normal. It's comparable to the magnesium and calcium, but this is a challenge. So all this post-lithium batteries can be made aqueous: sodium, zinc, calcium, and potassium, magnesium, aluminum. So there's a lot of research ongoing to make a aqueous battery for this thing. Then you do not need a glove box. They also reduce significantly the fabrication cost. So you know that most of the lithium battery, as you know, that the 20% of the cost goes to electro materials. The 70% goes to other parts. The packaging, the safety, and the other thermal management part. So actually, safety and the cost is kind of balanced for all these batteries. Depends on applications, right? So come to zinc-ion batteries. It start to become very, very, very hot since 2018. Okay, so if you look at the number of papers up to 2020, it's really rocking up, right? And the number of citations also. So whenever I review papers about zinc-ion batteries, I can see a lot of familiar names. And all those guys published papers, let's say in 2018, then got very, very high citations. So you can see that the citation number is also increases sharply. And then if you look at a review of review papers, okay, this is my own review of review papers on zinc batteries. It's a lot of people get interested, fascinated, and try to write review on zinc battery, but not all reviews are good, right? So nowadays, there's a lot of good reviews on first, most of the reviews is focused on cathode, because of cathode, a lot of materials, and people thought, okay, cathode is a challenge like lithium batteries. But when it comes to, if you compare to lithium metal batteries, then we also have dendrite problems. Actually, zinc alkaline batteries, the primary battery have dendrites. So later on, a lot of reviews on anode side, okay? And then later on, people come to electrolyte because people realize that, okay, it's more important to regulate the interfaces by engineering the electrolytes. So there's also good reviews on electrolytes engineering. So now come to outline of my talk. I tried to skip a lot of introductions, backgrounds, okay? First, the popular rechargeable zinc-based devices. So all this kind of devices are being pursued by people. For example, we have a normal zinc-ion batteries, okay? Zinc magnesium electrolytic batteries, which is the first appeared in 2019, pioneered by Dongliang Chao. And also have a zinc-air battery, which is not a very new topic, but still a lot of challenge, right? The main challenge is the cathode side. And then we have zinc-ion hybrid devices, which means we have a dual ions. Okay? You have a multiple cations, or even including the anions, shuttling between the two electrolytes. So in this one, this is kind of a similar concept to lithium and sodium dual ion batteries that people have done before. Okay, it's just it's a concept. May not be very good choices, but it's an interesting thing to do also. And people can also make this kind of micro devices using a finger cross electrodes, and also people can make very beautiful fiber batteries. Okay, for certain applications in wearable and textile devices. Okay. And zinc-ion batteries, we know that the zinc is suitable for aqueous batteries because the overpotential for HEI is relatively high, although we say that it's not completely high. It's completely sufficient. It still has some problems. So it's more suitable for aqueous battery compared to those other alkaline metals that have a very low overpotentials. And the danger is always an issue, especially in alkaline solutions. But when it comes to the neutral and weak acid electrolytes, it's not really that serious, although we still have dangerous. Where is my laser pointer? Okay, so although in neutral or weak acid, it's not as serious as in alkaline, but still we have these danger issues. And the cooling efficiency usually is higher compared to the primary alkaline batteries in weak acid. So that's why nowadays most of the zinc-ion batteries actually is made on weak acid. Cannot be too acid, right? And compared to lithium battery using organic electrolytes, of course, zinc-ion batteries use aqueous. And just yesterday, I received a paper for Maturity Energy. There's a group that do the other way, opposite way. They're still using the organic electrolytes for zinc-ion batteries, and then of course you can get very high voltage, high energy densities, but probably lose the priority in safeties. So this is a schematic diagram from Linda NASA in Jewel to summarize all the cathode materials and the related reaction mechanisms and how people try to engineer the cathode materials to stabilize them. And still NASA in 2016, they used the first time the layered zinc vanadate later structures and find that water actually involves the reactions in and out. So at that time, probably water is just regarded as a peel effect to stabilize the two layer structures. And later on, people also realized that actually water also try to have a screen effect to promote zinc ions integrations. And if you look at all the different reactions of zinc-ion battery, it can be very different depending on electrolytes, depending on the pH values. But let's focus on let's say tunnel structure of magnesium oxide. We have overall 4 types of mechanism categories. First is very simple zinc insertion and extractions. Okay, we just take the tunnel structure for examples. Other phases may have conversion reactions. Okay, let's just focus on insertion. So for this one, we say that zinc ions shuttle between anode and cathode. So this is a conventional work and shell mechanisms. And then later on, people find that, oh, depending on pH values, you may also have this zinc alkaline sulfate byproducts, which is later byproducts, which is because of the local water splitting reaction near the cathode surfaces. So in this case, people realize, oh, there's a proton goes in and out. Proton may promote this conversion reactions to manganese oxide, and later on may also have insertion reactions. So in this case, is have a zinc and a proton co-insertion process. There's also scenarios that is the number of papers publication on this topic is relatively smaller, but there's such scenarios that on the cathode side we have other metal cations goes into the reactions, whereas there's no zinc. So zinc just stay on the anode side. So this is kind of a hybrid process because of dual carriers. And we have this electrolytic process, okay? So electrolytic process means that so the magnetism does not stick to the current collectors anymore. It can be just dissolved into it. So this is the same process as a zinc anode, position and dissolutions, okay? So that means that both sides can have a dissolution, resolution, and a solution redeposition and dissolution processes. So this realizes the two magnetism 2+ and 4+ conversions, okay? So this is conversion reactions. So we can call it a conversion reaction battery, but we can also call it electrolytic batteries, okay? And because of this, people think, for example, this is an example of the dual ion battery. For example, sodium ion is using a typical sodium cathode, okay? Sodium battery cathode. And this one is also pioneered by Donny Chao that he used this 3-dimensional graphene foam as a current collectors on both sides, okay? And manganese 2 actually is kind of manganese oxide 2, which is 4+, can dissolve into the electrolyte in a certain pH values. So the very important is to control the pH values. And for aqueous batteries, the most important thing is electrochemical stability windows, right? So this is a similar case for PEC. For the electrochemical cells, for semiconductor, we need a conduction band and valence band sit across the water splitting potentials. But in this case, we should do opposite. We should not let the electron materials go beyond the OER or HERs. So you have to redesign. You have to select the proper materials. But usually, you cannot just choose you cannot sacrifice energy density by choosing a material just sit in between the HER OERs. So what people do is try to engineer the surface in order to increase the energy densities. So the overall open circuit voltage can be determined, although we can say that it's determined by the cathode anode side, right? Cathode minus anode or HOMO minus LUMOS. But actually, it's also determined, it's limited by the stability of aqueous electrolytes in the solution. So overall, we can use the overpotential on the OER side, cathode side, minus overpotential on the anode side, okay, which is zinc side, plus overpotential on the interface of the cathode and as well as the electrolyte itself, okay. So in order to overcome the intrinsic limit of the water instabilities, people do surface passivations to increase overpotentials, or people try to search new redox couples, which either with a faster reaction kinetics to compete with HROER, or they can have high overpotentials. Okay, so this is some examples. You can choose the different cathode anode side the redox couples to expand the electrochemical stability windows. Okay, and look at this. Come back to the electrolytic aqueous zinc manganese oxide batteries. So in 2019, there's 3 papers comes out one after another. The first one is Donny Chao. He published in Anguan Chemie, realized that if you charge batteries at constant voltage at high voltage and then let it discharge, if you charge at high voltage 2.2 volt and let it discharge, depending on the pH value, depending on the concentration of the zinc sulfate, they find that the discharge potential can be very different until finally get very, very nice plateaus. And immediately after, Zhi Chunyi group in Hong Kong, City University of Hong Kong, they also find similar mechanisms, and as well as Professor Xia Yongyao group in Fudan, they also find some similar. And in Xia Yongyao group, they also predict that it's possible to have electrode-free batteries. So that's basically redox flow batteries. So important thing here is control the pH values and the concentration of the manganese sulfate. Okay. And because of that, I would say that this is kind of very good news towards the zinc manganese flow batteries. So if you both sides is just put on current collectors without active materials at all pre-deposit on it, or just put this active material in a solution, zinc sulfate, manganese sulfate, then you can have a redeposition and dissolution process on both sides. So basically that's the concept of the flow batteries. But actually, commercialization of flow batteries has a lot of problems, especially in terms of the cost, in terms of the efficiency, in terms of the dangerous issues on zinc side. So there's still a lot of work, right? And but still, there's some prototypes, very promising prototypes. For example, in the Anguan Chemie paper in 2019, Donny already showed a very simple prototype to charge phones. And in 2020 or 19, Advanced Energy Material Cui Yi's group also demonstrated slightly larger prototype devices of the flow batteries. So as I mentioned just now, that all this aqueous battery has a limited working voltage. So later on, there's another group also in 2020, early 2020, published in Advanced Energy Materials. They put a membrane in between to separate. This is also a concept borrowed from photoelectrochemical cells, okay, photocatalyst water splittings. So people try to separate the electrode on both sides, and so on zinc side can be slightly alkaline, and whereas for the cathode side can be slightly acid, because if the whole thing is too acid, the zinc is unstable. So if they decouple the electrode on both sides, then you can eventually increase the over potentials and get a very large voltage beyond even 3 volt. Okay, if you put the two membranes, put an aqueous electrode between, even can go beyond 3.4 volt. So this is kind of engineering. It's a very innovative methods to realize high voltage. So now I'll give you some examples. Maybe elaborate a little more about cathode side, including both organic and inorganic cathode side. So in 2018, luckily we published the first review articles on zinc-ion batteries, recent advance in zinc-ion batteries. We summarize all the different kind of polymorphs, crystal polymorphs of zinc and manganese and vanadiums, in addition, as well as some organic like Prussian blue and mauve and some other organic cathode materials. So we say that there's a various crystal polymorphs, and this different crystal may have a different reaction mechanisms, especially for manganese also. We now realize that there's many, many different possibilities. And we also have cathode instability issues, right? The cathode material can be structurally, can have a phase transitions during the first discharge. And the phase transition sometimes is irreversible, and a layered structure may become a non-layered, right? If the structure is not engineered by pillar effect. And they may also have dissolved problems. So most manganese and vanadium cathode are dissolvable, are soluble in the aqueous solutions. Failure of the batteries due to zinc dendrite growth, as well as corrosion. So corrosion is a very evident phenomenon for zinc anodes, okay, because of the water splitting reaction, because of local pH values, right? Increase of pH values, decrease. And also because of aqueous nature, they have a low operating voltage. So this is a key problems of the faced by the aqueous zinc-ion batteries. Okay. And 2018, we have the first work that we tried to replace both anode and cathode side with a 3-dimensional array structures. So make arrays of zinc alkaline vanadium cathode, which is about 5 micron height nanosheet structures. On the anode side, instead of using the common zinc foil, we replace with a zinc plate, hexagonal plates, electrode deposited on a 3-dimensional graphene form. Anode side. Actually, this material does not necessarily mean it's low mass loading. The mass loading can be even higher compared to the dense 2-dimensional films. But more importantly, it can increase the DOD, depth of discharge, and have a better utilization ratio of zinc. So we make a quasi-solid state zinc-ion batteries based on this array structure on both cathode and anode, and find that the energy density at that time can outperform a lot of other full batteries by including both cathode and anode mass. Also can go to very high rates because of the array structures. And recently was a collaboration with a guy from from Genie University. They make this high mass loading vanadium oxide 3.7 with a crystal waters nanosheets. So this is also very high mass loading array structures using this kind of a one-step hydrothermal methods. So they grow materials with different mass loadings and then identify the mass loading about 5 point something. Okay. And the more important contribution of the work is that they use various calculation tools to verify the 2-step reaction processes, 5 to 4 and 4 to 3, and redox reaction for vanadium oxide. Although this kind of redox peak actually is very common for other vanadium polymorphs, right? So they also did a DFT calculation to confirm how zinc ions goes in and out, and find that zinc ion prefers to occupy site 1, corresponding lowest potential energies. And if you do ex situ Raman XRD, as well as ex situ high resolution TM to confirm the crystal phase, which is a reversible crystal phase. And then we do the fully charged, and somewhere in the middle, the XPS find the peak is is coming back after charging, and the XRD peaks also is reversible. Okay, so this verifies the two-step redox peaks of vanadium because of vanadium-5. Okay. Recently, we also work collaborating with Professor Zhang Xichun in City University of Hong Kong. Professor Zhang is very good at is organic chemist, so he's very good at making organic materials. So I have a postdoc transfer from his group to my group, continue this work. So they find that some of the organic materials, if they have this function group, this oxygen and sulfur moieties, they are able to interact with the zinc ions by donating electrons. Okay, so I mean, if this reaction is reversible, if this reaction is reversible, and if the voltage is not that bad, then it can be used as a battery cathode. But most organic materials has a relatively low, no more than 1.5 volts, sometimes even just 1.0 volt. Okay. So in this work, we developed this fabricate, this is a PDBS polymers. Okay, it's kind of a polymer chains to host zinc ions. Of course, before the polymer chains, this is the precursor materials. We also check the precursor material. Actually, they can also interact with the zinc, but the problem is that the hysteresis, the polarization is huge. Okay, we don't want this. So if you make the polymer chain, find that the polarization can slightly be lower. Although, let's not put too much attention to the voltage profile. The voltage is quite low, right? It is not really cathode materials. And so there's a lot of simulation and characterization try to understand what is the advantage of polymers and how the zinc interact with the function groups. Okay, and find that they can do this electron density gradient maps. Find that whether there's a charge interaction between zinc and oxygen, and between zinc and sulfur, to confirm that okay, there's some electron clouds sharing by those two guys. So that means we may have a bonding interaction between this oxygen sulfur with the zinc, causes the charge transfers, so contributing to zinc ion storage. And for example, this is two units of the polymer chains. So we have the zinc on one of the benzyne, the other is on the other benzyne, and somewhere is in between. Okay, this is between. So we have say 3 zinc ions is integrated into this one unit. Okay. And also because the polymer chain is rotable, is rotatable. Okay, is rotatable during the process. So that means if zinc ions goes in and out, it may cause the rotation to have a better accommodation of zinc ions. So this is of course based on the thermodynamic molecular dynamic simulations to find the most stable structures after uptake of zinc ions. Okay, and actually, if we do the cathode materials, if we do organic cathode materials, we also borrow all the concept from inorganic. We know that for vanadiums, for manganese, we have the protons in and out, right? So proton is very common phenomenon in the manganese oxide tunnel structures. So sometimes proton may interact, have a conversion reaction first to change the crystal structures. We find that actually even in organic cathode, the proton may also go in and out, have some interaction with the functional groups. For example, maybe in the first step, the proton goes in, form a bonding with oxygen, and later on the zinc comes in. Okay, so this can be confirmed indirectly from the differential charge and discharge curve to find that okay, we have a zinc. The first cycle we have a zinc, also have a proton. In the fifth cycle, okay, in the fifth cycle of charge, then the peak redox peak corresponding to proton is much reduced. So the peak corresponding to zinc uptake is more dominating. So that means maybe the proton comes in only in the first few cycles. It will not be dominating in the subsequent cycles. Okay. Also the same cases here for discharge. Okay. So that this proton may causes some interaction at the first, but zinc will dominate in the futures. Okay. Of course, this is a preliminary data. So we may think that this process may occur to many cathode materials as long as we deal with aqueous electrolytes. Okay. And come to zinc anode. The zinc anode becomes more interesting compared to cathode in the first few years. Okay. And if you compare lithium, sodium, potassium, magnesium, cathode, and zinc, so zinc when standard potential, okay, wins out is here. Okay, this is zinc compared to lithium, compared to sodium peak, and the cost, of course, is very low. Okay, and the abundance may not be compatible to, but actually it's higher than lithium and sodium and potassium. Okay, zinc is even edible, right? It's very safe. And the hydroactive ion radius is a challenge for zinc. It's here, right? So it's not a good thing. So you need to overcome. And the capacity density and specific capacity is not the highest, but okay, the capacity density is okay. Volume density is okay. But specific capacity is 800 something. It is okay, but not comparable to lithium and lithium metals and other potassium metals. And but the major issue of zinc is not the worry of the capacity and the density is not big worries. Okay, the big worry is the stabilities. Okay, and people know that for alkaline electrolytes, from alkaline electrolytes, we have many issues. We have a corrosion because of the pH value. Corrosion, we have dendrites because of inhomogeneous deposition of zinc from the electrolytes. And we may also have this kind of hydrogen evolution reactions, okay, generates bubbles. This phenomenon is very severe in alkaline, but also evident in mild electrolytes, mild electrolyte neutral and weakly acid electrolytes. Because all this are observed either just by in situ photo. Okay, you can see the bubble generations. And SEM image can also show this zinc alkaline sulfate byproducts. Okay, this so-called ZBS byproducts. And sometimes the byproducts can be reversible, can be irreversible, depending on how you manipulate the electrolytes, right? If this guy is irreversible, just cover the surface. You can cover both cathode and cover both anode, both cathode and anode side. If the cover surface it consumes the charge, right? It consumes alkalines, and also it consumes a cover surface become insulating. So people have to try to avoid, eliminate this stuff. Okay, so so there's a lot of challenges there. So what people do, try to deal with this challenge, and people do various kind of things. Can do epitaxial metal electro deposition of the zinc on a epitaxial graphene sheets. This is a paper published on Science, and Professor Zhi Shuyin from City University of Hong Kong, they coat a very thin layer. Maybe it's also it's a porous calcium cassette layers on the surface, inorganic layers. Try to tune the interface potentials. Okay, and other one, let's say, is a MOF. Is a MOF PVDF polymer, organic plus polymer coating on the surface. Is a very, let's say, it's very flexible and soft surface, which allows the zinc ions penetrate through and isolates the direct contact with the waters. And also there's a three-dimensional eutectic zinc aluminum alloy, and they have this kind of three-dimensional hole structure. And this holes sort of have a electrostatic shielding effect. Okay, so make the zinc will not just goes to the sharp points or be spreading uniformly. So actually, the other strategies is to make a three-dimensional zinc. So there's a reason behind people think that if you make a three-dimensional zinc, the local electric field will be lowered effectively compared to the flat surfaces. So that's why actually a lot of work, if you do not want to make a dendrites issues, then you go to three-dimensional zinc. But if you really want to make a story out of zinc, then you go to a zinc foil, right? But interestingly, if you look at all this work, people try to coat the surface to increase the water hydrophilicity, make the surface wettable by waters, right? So all the different mechanisms are summarized here. Okay, and but the problem, for example, this is the work by Professor Cui Guanglei in Qingdao. They coat the surface with this polyamide, PA, which is a polymer layer. They say that this PA makes the surface more wettable and suppress the corrosion problems. Okay, but actually, we also try to do something similar. It's probably just a play. We call the surface KS6 is some materials, and make the surface actually hydrophobic. Okay? This makes the surface less wettable. But we also find that we have the similar effect. Okay, the surface have less this kind of spikes and dendrites is less severe compared to bare zinc. So sometimes we find that a surface coating passivation layers is not just simply make the surface wettable by the electrolytes. It may have some other effects, and the overall performance, the dendrite self-corrosion, is a result of multiple factors. Okay, the multiple factors I try to summarize here. You may increase the hydrophilicity, yes, of water electrolyte. You want to have a good contact, and it may avoid the contact with the water directly. You coat the surface so the zinc surface will not direct contact with the water, and it lowers the water activities. Okay. So if you increase hydrophilicity, that means what? That means, okay, there's more electron ions can come to the surface and that penetrate through your passivation layers. Okay. And so it actually increases, you must have good ion conductivities. And also you reach the surface effective size for uniform zinc nucleation. This is the effect demonstrated by Cui Guanglei in this work. So they have they increase the density of the nucleation size, so have a more uniform depositions. And another effect, we think that maybe, okay, this passivation layer dependent interface chemistry, it may lower the water activities. So it's sort of anti-catalysis effect. For example, in 2018, again, we use a three-dimensional zinc to find that compared to zinc foil, the surface do not have a very, very sphere agglomerations of zinc compared to the zinc foils. And the symmetrical CL also shows a very stable voltage profiles. Professor Chao, you can stop me. You can give me a hint if I use too much time. And some other zinc devices we work because we want to make some new concept rather than just follow people. So we're really not compatible with all the group in China. They are too fast. So we borrow a new concept that we think that if the battery got too hot, right? Especially in lithium metals, if the battery goes too hot, then have some problems. And people try to make the batteries work in high temperature and low temperature. If you go to north part of China, you want the battery to still work. Okay. And then we think that how to make it hot. Aqueous batteries, the aqueous batteries contains water. Water can evaporate at high temperatures. So we think, okay, we'll make a battery that we use the hydrogels containing water, electrolyte, waters, and the polymers. So this water make it evaporate, can penetrate through this this cathode. The cathode is made as permeable. The water vapor can penetrate through. And then if the temperature cools down, so when the water leaves the electrolytes, then it will not work, right? Because the ion conductivity is much reduced. But then if it cools down, the water can be reabsorbed into the batteries and recovers the battery. So this is just a concept. It works. The concept actually that, for example, the temperature highest in just 50 degrees from 20 degree increase to 50 degree, the capacity drops to almost zero. It doesn't mean the battery is dead. It's just a take a rest. It's just a take a break. And then if the temperature goes lower back again to 25 degree, it takes 3 hours or even 3 hours to recover. Of course, this recovery time is too long. It's way long, right? You don't want to wait 6 hours. But it's just it's a demonstration, proof of concept demonstration of the concept. If you better design the polymers, better design the packaging of the cathode and anode, maybe have a better, higher recoveries. And then we can also make a printable zinc-ion batteries. So we print tungsten oxide. So this work contribution actually is to develop the ink for inkjet printings. The print tungsten oxide thin films, so the thin films are very stable, and use a zinc anode, zinc foil as anode. It can produce a zinc-ion battery, which is also electrochromic. So if at different charge states, they have a different colors, transparencies. Okay. And people also make zinc-ion capacitors, right? Zinc-ion capacitor means that you have a zinc anode, and the cathode make a carbons, right? Cathode is made of carbon, so this carbon must have be able to capture the anions from the electrolytes, and also should have a high surface area and high potentials. So this work is in collaboration with my previous postdoc Wang Huangwen in Wuhan. So they fabricate in one very higher yield of this kind of a hollow bowl-like carbon surface with a lot of metal pores on the surfaces. Okay, they can tune the morphology by tuning the ratio of the precursors. Of course, actually, this is a very well-established process in the literatures. So we just apply this kind of a hollow bowl-like carbon as cathode materials as cathode for the zinc-ion capacitors. So this work mechanism is actually quite simple. We just borrow the mechanism from the lithium-sodium ion capacitors. So zinc have a dissolution, have a solution and redeposition on this side. So ions goes into positive ions go this side, and the anions goes to the other side. So it's a dual ion process. So we'll compare to the carbon black. I find that there's a little bit dendrites, but not so serious. This is ZHS, zinc alkaline sulfate flakes, right? And we want to say that actually there's some debates here. Okay, there's some debates here about the working mechanisms. If you just use the mechanism from lithium, sodium, and capacitor, it's just like that. It's very simple. Okay, but then if you look at some process, some other papers I read, including Professor Liu Xihong, including Professor Wang Guoxiu, they try to say that actually this cathode material can also absorb cations. Okay, let's say during charge it can absorb anions, and during discharge it can absorb cations. So it can. If this mechanism it really works, if it's so far not proven yet, really, but it's kind of proposals. But I think if it's really proven workable, this is a different mechanisms. Okay, and I think I'm pretty. So I give a summary that aqueous zinc battery is very interesting. You have a lot of challenges. You have a structure instability. You have a poor electroconductivities compared to most of the cathode, especially organic one. You have a dissolution of active materials, magnesium, vanadiums, all this are soluble. And we have electrostatic interaction with the zinc ions in the cathode. So this electrostatic repulsion is very strong. It can causes very sluggish kinetics. So that's why people put crystal waters or put some metal cations into the cathode materials to reduce this strong repulsion interactions. And also water splitting reactions. This is the most serious issues for aqueous batteries with water splittings, OER and HERs, and we have zinc dendrites. So we have challenges, then we have opportunities, right? We have a very complicated process in such a simple systems, but then we have more things to play with. So the big question we ask ourselves, what is next? So what is interesting to me is that this conversion type reactions actually is quite interesting using this pure dissolution and redeposition redox couples is quite interesting. It's very different mechanism compared to conventional intercalation reactions, and the voltage can be very high. So with that, I would like to thank all the students and postdocs in my group, as well as the collaborators at funding agencies. And also, I would like to thank your time, as well as Professor Chao and other chairs for inviting me during this very high-level symposiums. Thank you very much.
Thank you. And it's a wonderful talk. It's so comprehensive and very, very educational. And,
yes,
do we have any questions from audience? It is the time to ask a quick 1 or 2 questions. And I do have one question. When you mention those manganese-based cathode that can give you a much higher energy density, and but what I know is the manganese-based material or cathode give you a serious dissolution issue.
Yeah, exactly.
And that's compromise the cycling stability issue.
Exactly, yeah. So that's why magnesium oxide actually may involve the phase transitions, or as I said, they can just dissolve into the electrolyte. That is why in the early days, people can get very high capacity than the theoretical values. And people don't understand. How come? It's actually exactly because of the dissolution reaction to go to electrolyte. Actually, you can also see the solution may got some colors. So later on, people try to use these disadvantages, make advantage of the problems, and to broaden the voltage. Okay.
So this is what they thought come from about the what is a flow battery.
Yeah, the wall-in salt is another strategy.
Okay. Yeah, I think. Well, any questions from audience?
Looking forward to Nanfeng's talk.
What? Yeah, no questions.
Can't wait.
Who was asking questions?
Let's check if there are any question in the chat box. If no, then I really pass the time to Nanfeng.
Yeah, there's no questions on the chat box. And
okay.
I think our speaker, Professor Fang, and it's a wonderful talk.
Thank you very much.
I just got a note from Dr. Guilin Wang that there are about 8,000 audience in other platforms and watch our presentations. So it's a big pressure on the speakers, and 8,000 people are watching you. And
are they waiting for me to sing a song? Or?
Well, it's a good idea. You can do that.
Next time. Okay.
If not,
thank you, Professor.
Okay.
Yeah.
Well, let's move to the next speaker, and Professor Nanfeng Zheng. And actually, among all those speakers, Nanfeng is if I remember correctly, is the only speaker I never met in person. So I emailed him yesterday evening, asked him, is there anything I should introduce him? And he was so conservative, reserved, and say nothing. And we look at his resume. He is really accomplished significantly, got all the awards in China. And we are very happy to have Nanfeng here. And I will remember next time I will visit you in Xiamen, the beautiful city there. Okay, the floor is yours.
Okay, thank you for the nice introduction. First of all, I would like to thank the organization's committee for the kind invitations. So in this talk, I'm going to share with you our recent results on surface coordination chemistry of metal nano catalyst. So I think for catalyst, we all already know that it's quite important for our chemical productions. And for heterogeneous catalyst, actually it's really important for chemical industry because 90% of the industry catalysts are heterogeneous. The main reason for that is that they can make a lot of money for us because they can be recyclables, they are highly stable. So unfortunately, they are not so active compared to homogeneous catalysts. So one approach to make them highly active is try to make those active components as small as possible. But once we make really small components, basically they are easily sintering, right? So in many cases, we try to deposit those fine particles on high surface area support. So the whole system actually is really complicated, right? We build up so many interface issues. So that's why there's mechanism are rather poor understood. So it's not so surprised they have poor selectivity. Okay, so and in the literature we have already observed or see so many nano effect for heterogeneous catalysis, size effect. A really typical example is regarding gold catalyst. We all know that gold is catalytically inactive, like in the bulk form. But if we deposit gold nanoparticle on high surface areas support, like oxide, like iron oxide, for example, actually we can make highly active catalyst, even for CO oxidation at very low temperature. And we also have many other effects like shape, support, you name it. Okay, many effects. Okay, so here is a TM image, typical TM image for gold nanoparticle supported on iron oxide. And at the left-hand side here is the low resolution TM. So this is the typicals. You can TM. You can see here the white dot here represents one nanoparticle. But with the development of advanced aberration characteristics TM. So besides this big particle, we can also see some single atom or even several atoms coming together to form this small cluster. So basically, all these species they will not be able to observe by using low resolution TM or conventional TM. But is really funny is that, you see, we can basically use sodium cyanide to etch out those gold nanoparticles. So, which means that if we use conventional TM, we will not be able to see anything, right? Nothing there. I mean the gold particle. But if we use this sample after etching for the water gas ship reaction, we observed quite similar activity. So what kind of feeling you have? Do we really believe what we see? No, right? So this is really like blind man and elephant, right? We only see part of this catalyst. So actually, for the fundamental and application of NATO's catalyst, they are really the issue across multiple size scale, right? So for the industrial application, they take place in macroscopic scales. But if we want to understand the catalysis mechanism, all these catalysis reaction, they take place at molecular scale, which is either sub-nano scales or nano scale, right? So it's not so surprise. You see, in the chemical industry using heterogeneous catalysts, although we are able to produce the desired product we want, but in many cases, we also generate undesired product as a pollutant. So in order to really prevent the production of this pollution, we really need to have deep understanding on how catalytic reaction taking place on the surface of nanocatalyst at the molecular level. Okay, so here I'd like to just show you one example. For example, we all know that gold is really easily to be oxidized, right, in airs, because gold, carbon dioxide, and cuprous oxide, they are not dense structures. So they cannot form condensed passivation layers on copper. So when we expose copper to air, they will continuously oxidize until we get highly oxidized copper surface, which can be covered by copper oxide. However, after years of study, we found that if we trace the surface of copper with fomate, and we found that those fomate can form a really robust passivation layers because we have the fomates binding to the copper surface, particularly on copper 1,1 surface. Basically, this passivation layer can prevent the absorption of chemical absorption of oxygen, which means that those oxygen won't be activated on the surface for the oxides formation. So with this understanding, basically, we can try to use copper to replace silver, for example, for printing electronics circuit, and also replacing the silvers in solar cells. So we are still working on the technology development for this field. So the reason why we'll be able to really get the understandings on how those fomates can form passivation layers on copper surface is because we have the help from Q+ FM, which help us to identify the bonding structure, the coordination bonding structure of the fomates on coppers. And with this binding structure information, then we can get deep understanding why this surface is good for the anti-oxidation. So in the field of heterogeneous catalysis, particularly if we use metal nanoparticles, in many cases, these catalysts are often surface modified by certain organic species or loaded on high surface area support to enhance their catalytic performance. So in past almost 10 years, our group has spent a lot of efforts to understand how this metal organic and metal inorganic interface enhance catalysis. But the challenging part for this kind of study is that we don't have good tools to really see the details, surface and interface structures of these nanomaterials at the molecular level. So what can we do? So the main strategy in our group is to try to build up some model nanocatalyst. And for this model nanocatalyst, they have well-defined surface and interface structure. So in the following slide, I'm just like to show you two examples. One example is atomically precise nanocluster. Okay, and this atomic precise nanocluster, they can be considered as a nano-size molecule. Okay, so they have well-defined composition and structures. And they can be recrystallized into single crystal, just like protein. Then we can use X-rays diffraction to identify their total structures, as well as by using some mass spectrometry and MMR techniques for the compositions identification. So here, I just like to show you one example. For example, this is a gold-44 clusters, and on the surface, we have three different kinds of ligand. One is bromine, the other one is nitrogen's heterocyclase carbene, another one is phenylacetylide. Okay, so on the surface, we can identify that we do have this gold plus 1 as the binding site of alkyne, of this alkyne. And because this carbene ligand is so bulky, and then on the surface, we have the open metal sites for water's binding. So which means that by using these clusters, we already have the binding site for the reactant, both reactant of alkynes and also water. So actually, it turns out this catalyst is highly active for the hydrolysis of alkyne. Okay, and as you can see here, we don't see the decrease in the activities, and they can be used for so many times. Okay, just because we have these surface binding sites. If we don't have this carbene, this bulky carbene, we don't have this activity at all because we don't have the surface open size for water. So the solution of this structure gives us a really clear image on how the catalysis is taking place on the surface. And more importantly, with this kind of model catalyst, we can understand how electronic structures of the reactant influence their catalysis. For example, for these alkynes with alkyl group, there are no any activity at all because the binding site is not good for this alkyne. That's the reason. And if we have strong electrons withdrawing group on the phenyl group, it's not good either because the binding is also weakened. So the model just gives us a really nice system to understand the catalysis process. Another model nanocatalyst is atomically precise, is atomically dispersed metal catalyst. And several years ago, so we developed an effective photochemical method to prepare atomic dispersed palladium on titanium oxide. Because all these palladium sites, they are atomically dispersed on support. And they have uniform coordination structures, environment. So we can use X-ray absorption spectroscopy to identify their local coordinations environment. So after the crystallization, basically, we found that the palladium is in the 4 coordinated and is bound by this ethylene glycolate together with waters. And with this coordination structure, basically, once we introduce hydrogen, the hydrogen can get activated into hydride and proton. This is quite interesting because if we want to do the hydrogenation of a carbon-oxygen bond, we do need proton and hydride, right? Because the oxygen here is more negative charge and the carbon here is more positive charge. So we do need the help from both hydride and proton. So that's why if we use this catalyst for the hydrogenation of this ketone, of this aldehyde, you see, we can see significant enhance in their activity. And even for the really simple reaction for the hydrogenation of styrene, okay, because we already know that the hydrogen can get activated into hydrides and proton. So if we replace this H2 by D2 or the solvent by deuterize solvent, you can see we can get 4 products. So which means that with this understanding, it's possible for us to finally control their selectivity, right, at the molecular levels. Here is another example. So alkaline doping is a really interesting method for us to promote heterogeneous catalysis, and it has been widely demonstrated in literature. However, why the alkaline doping can promote the catalysis is still under debate. So in this example, we prepare atomic dispersed ruthenium with either sodium hydroxide or ammonium as a precipitate, as a precipitator. So as you can see here, for these both catalysts, either use sodium hydroxide or ammonium, they have quite similar initial catalytic activity, right? Unfortunately, because the hydrogenation reactions will carry out at rather high temperatures with under the high pressure of hydrogen, as you can see here, for a catalyst with ammonium, we see the significant decrease in the activities. But for this sodium-doped catalyst, the stability is quite good. So the reason for that is that after a careful X-ray absorption spectroscopy study, we found that when we use ammonium to prepare the catalyst, the ruthenium can get reduced into ruthenium zeros nanoparticle. However, for the ruthenium catalyst prepared by sodium hydroxide, basically they still keep, after the catalysis, they are still atomic dispersed on the surface. So that's the main reason. So the ruthenium +3 is the active site for this reaction. So the main reason why the sodium can stabilize this atomic dispersed catalyst is because we have the strong coordination of this sodium cation with hydrides on ruthenium +3. And this interaction actually can stabilize this hydride species. And what's even more interesting is that besides preventing the reduction growth of ruthenium +3 into ruthenium zeros, we also found that this interaction can reduce the energy of the transition state of hydrogenation reaction. Do we have any experimental evidence? The answer is yes. So in most hydrogenation catalysis, if we replace the hydrogen by D2, by deuterium. So because the deuterium is more heavy than hydrogen, normally we see the decrease in their activity. But in this case, we found that actually the use of deuteriums can enhance the activity. It's mainly because we reduce the energy barriers of the reaction. So indeed, we have the evidence for our proposals. And simultaneously, this electronic static interaction can also enhance hydrogenation activity just because it reduces the hydrogenation energy barriers. So that's why this catalyst is highly active for the hydrogenation of benzene ring and as well as pyridine rings. So it's really powerful and stable. So in the following slide, I think I'm going to just like to focus on selective hydrogenation of two kinds of species. One is carbon triple bond. The other one is nitroaromatic. Why I'm going to focus on these two reactions? Because they are quite important. Because for the semi-hydrogenation of these carbon-carbon triple bonds, they can find so many inductory applications in, for example, synthesis of vitamins and also others, many drug molecules. However, for the hydrogenation of these carbon-carbon triple bond, basically we can have 4 hydrogen added to this triple bond, right? But thermodynamically, the addition of hydrogen to triple bond to form double bond, and also from double bond to single bond, the thermodynamics are quite similar. So which means that it's rather difficult to really stop the reactions at the double bond. Okay, so how can we do that? So in our inductors, they already develop already effective catalyst, which is Lindlar catalyst. They try to poison the surface by using lead or other organic modifiers. Okay, they modify the surface, they poison the surface, they reduce the reaction rate so that they have a chance to stop the reaction at the single bond, at the double bond. But the disadvantage of this technique is that we need to lower down the reaction rate. Several years ago, actually, this is a totally unexpected result. Initially, we tried to modify the palladium surface with a thiol. So basically, we treat these palladium nanoseeds. The thickness is only 5 atomic layers. Okay, because we make this material like more than 10 years ago in our group. And so after treating, as you can see here, all these nanoseeds, initially it's hexagonal, right? But after that, it's highly distorted. So what's the reason for that? So because the thickness is so small, we will be able to use X-ray absorption spectroscopy to resolve the structures. And after careful studies, we found that actually the palladium can cleave part of this sulfide carbon bond. So some of the sulfide, they just penetrate into the palladium lattice. So that's why the palladium seeds get highly distorted. But on the surface, we still have the silase modification. So from this structure, basically, I think you might already have some chemical picture in your mind, right? So the silase, they must create some stereo effect, right? And the penetration of this sulfide into the palladium lattice, they should create some electronic effect because palladiums, the lattice has been changed. So unexpectedly, as you can see here, when we use the highly distorted palladium nanoseeds as the catalyst for the semi-hydrogenation of this internal alkyne, as you can see here, we get very high selectivity. We only get these double bonds intermediates. So I think this is quite easy to be understood, right? Because we create static effect. And this static effect hindrance can prevent the absorption of these double bond species because they are more bulky, right? But what is not quite understandable is that we didn't decrease much of the activity of this catalyst, didn't see much decrease in the activity. The main reason for that, actually, based on our DFT calculation, is that because we have the formation of palladium sulfide, and the formation of this palladium sulfide species can weaken the bonding of the hydrogen on palladium. So which means that this hydrogen species can easily migrate to the intermediate, to the substance for the reaction. So that's why. So after this understanding, actually, the whole picture is rather simple. So the silates create a static hindrance to prevent the further hydrogenation of alkene, and the electronic structures created by the formation of palladium sulfide actually promote the catalysis. So we don't have the trade-off between activities and selectivity, right? However, the modification of the silate, the static hindrance is not big enough for the terminals alkyne, because this alkyne actually can easily, even we have small space, they still can interact with the palladium surface. So how can we solve this issue? So we consider if we will be able to minimize the palladium size into single atom, we should be able to resolve this issue, right? Because the bonding of this alkyne to the single atom of palladium should get weakened. So we try to use electrochemical approach through this galvanic replacement. So we can use copper 2 oxides react with palladium 2 precursors, because based on the redox potentials, they can do the redox reactions. Or we can use metallic copper for the replacement. And we found that actually by using these tools as support, we will be able to deposit palladium either on copper 2 oxides as palladium +1. And the oxidation of this palladium actually can be detected by using CO as a probe using FTIR. And on this metallic copper, as you can see here, actually the CO's vibration frequency, the wave number is much lower than the ones on copper 2 oxides, just because there's difference in their oxidation state. So basically, we have, and you might know that for the copper 2 oxides, for all these coppers, they are they are in two coordinated structures and linearly two coordinated. So if we put palladium in to replace this copper, they will keep this +1s and two coordinated structures, which is confirmed by our X-ray absorption spectroscopy studies. So, and both their oxidation states and also the coordination structures. But if we try to put palladiums on other support, like titanium oxide, zinc oxide, or aluminum oxide, they are in 4 coordinated structures and +2. So it's total difference. So we use this catalyst for the semi-hydrogenation of this phenylacetylene. As you can see here, we mainly attempt these styrene as the products. And this is what we expected, because we reduce the domain size of the catalytic metals. And why we will be able to use this palladium +1 for the reaction, because this palladium +1 is still active for the hydrogen activation. Because for this copper 2 oxide, they have strong basicities. So the hydrogen can get activated on the palladium through heterolytic activation pathway to form hydrides on palladium and proton on oxygen on copper 2 oxides. And we do have the FTI evidence to prove this. So why we only get these styrene as the product? Our DFT calculation suggests that because for the hydrogenation of triple bond, we can have 4 hydrogen added to this triple bond. But our DFT calculation suggests that the third hydrogen can be inserted into double bond intermediate, but the fourth one, the energy barrier is really high. So the first one actually is the proton transformation from copper oxides to this intermediate, hydrogenation intermediate with the third hydrogen added to the double bond species. So this turns out to be quite interesting, right? Because can we really prove this? The answer is that yes. The answer is yes, because we already proved this. So how can we do that? So basically, we try to replace the hydrogens by D2s after 100% conversion of this phenylacetylide. Because at this point, we already get styrene. So if we have the third the addition of third hydrogen, which means that the double bond should be open, right? So, and then the single bond should be rotatable, okay? So we found that actually after we replace the hydrogen atmospheres with D2 atmospheres, we did see that we can do the hydrogen and deuterium exchange. So this really proves that our DFT calculation result is correct. We do have the addition of third hydrogen, but not the fourth one. So after this understanding, basically we found that this catalyst is highly active for all kinds of terminals kind. Okay, so this is quite interesting. Another interesting phenomenon we want to get deep understanding is regarding hydrogen spillover. In catalysis, a lot of demonstration already prove that once hydrogen molecule get activated into hydrogen atom, and this hydrogen atom can spill over on metals easily. Then our question is, once this hydrogen atom spill over to other metal, if we can utilize those hydrogen atoms for hydrogenation, which means that we might not need to use palladium for the reaction, right? Because the price for palladium is like, I think it's more than 500 yen RMB already. But the price for copper is like 6 cents RMB. Big difference, right? So how can we really prove this concept? If we can use hydrogen spillover to do the reaction. So we found that actually the speed hydrogenation is highly dependent on phases of the metal. So basically, in our design, we try to use copper nanotubes with 101 as exposure surface, as well as nanocube with 100 surface as the exposure surface. Okay, and we found that actually, indeed, based on our DFT calculation with Professor Gang Fu, and we found that on copper 1-on-1, actually the energy barrier, the reaction energy barrier is pretty low. So which means that once hydrogen molecule get activated on palladium, they activate it into hydrogen atom. They can spill over to copper surface. On copper 100, they can do the hydrogenation. Okay, so how can we prove this? So what we did is rather simple. So as you can see here, after we prepare these two catalysts, and indeed we found that the palladium on copper 100 is more active, although they have the same palladium loading amount. In particular, when the palladium is highly diluted, right? If it's highly diluted on copper 1-on-1, it's not active at all. But if it's on 100, it's highly active. So this is quite interesting. It really suggests that our DFT calculation is quite reliable, right? And another experiment, what we try is to you see, we have this palladium copper 1 catalyst, and then we add additional copper 100, which is not active themselves at all. You see, we add one portion, we increase the activity. Another portion increase the activity. So which means that the copper 00 really active for the hydrogenation. Okay, so this is quite interesting. And this phenomenon is also confirmed by carbon monoxide poisoning. You see, we introduce carbon monoxide, we can decrease slightly the activity, but the activity is only completely disappears only after all the palladium get poisoned. Okay, so with this, basically, we found that it's possible to really decrease the loading of the palladium down to 50%. 50 ppm. So this is quite interesting, right? So we can lower down the loading of this palladium with a high price and replace it by copper. So another interesting reactions we have been trying so many years in our group is the hydrogenation of nitroaromatic, because nitrogen containing compounds are so important. For example, more than 80% of FDA approved drug contains nitrogen atom. And many of these nitrogen containing species are made from the hydrogenation of nitroaromatic. But actually, the process is rather complicated. You see, although we might only want to guess aniline, amines as the final product, but during the process, we might generate other byproduct. So how can we really prevent the formation of this byproduct? Okay, so several years ago, so we tried to use this palladium platinum nanowires as the model catalyst. And I would like to mention here is that all these nanowire, their surface are only covered by ethylene diamine. Okay, so initially we consider this shape is so important. But after years of study, we realized that the shape is not important at all. It's because we have the bonding of ethylene diamine on their surface. So this nanowire is quite unique in the hydrogenation of nitroaromatic. We only get this hydroxy aniline. This is quite unusual because the further hydrogenation of hydroxy aniline to aniline is so thermodynamically variable. Why we only get this hydroxy aniline? Okay, so you see, they can be recycled for many times. If we use unmodified PT catalyst, we always see the decrease in their selectivity with the increase of the activity and the conversion. Okay, so how can why these nanowire are so unique? So after careful X-ray absorption spectroscopy study, TEM, and as well as DFT calculation, we found that for these nanowires, although we have actin diabine bind on their surface, but their surface still have some exposure size. And we all know that if we want to have the metal bind with ligand, basically their d orbital need to have empty d orbital, right? But for PT, their d orbital is already fully occupied. So how can this palladium atom be used to coordinate it to actin diabine? So one way to do that is to push their d electron to the neighboring palladium atom. So which means that all the surface uncoordinated PT sites can be electron rich. Okay, so with this DFT calculation result, then we try to use carbon monoxide as a probe. You see, if the surface is electron rich, which means that we have more electron can back donating to anti-orbital of carbon monoxide, right? So in this, our CO stripping experiment suggests that with the bonding of the actin diabine, we do see the much enhanced CO binding on the surface. And the enhanced binding strength is also proved by our DFTs, FTIR's measurements. So because the wave number of the carbon monoxide vibration has been changed. So actually, with this in mind, I think the mechanism is quite simple. We have a binding of actin diabine. Then we can induce the formation of electron-rich surface. So all those exposure sites, they are more electron-rich. So for this, nitroaromatic is electron deficient. So they like to bind on this electron-rich surface. And though still electron deficient, so they can bind to the surface. But once we form hydroxy aniline, it's electron-rich. Sorry, they are not welcomed by electron. They are not welcomed by this electron-rich surface. So they are taken out from the surface. So that's why nanowire is not important. So the actin diabine is so important. So that's why we can use a palladium black, platinum black, and then modify it with actin diabine. Then we can switch their selectivity. So this concept actually has been already used for many important intermediates production in industries like these peptide intermediates, and it turns out it's quite effective. So another approach is to introduce metal inorganic interface. Several years ago, so we have demonstrated that if we deposit iron hydroxides on PT, then create a really interesting interfacial size, which can do those coupling eliminations of carbon monoxides. So in this case, basically, the interfacial hydroxide can react with carbon monoxide, which is a reducing agent. So with this understanding, actually, we found that it's also possible to use this interface for the selective hydrogenation of these nitroaromatics. So the reaction is rather simple. You see, here is carbon monoxide. We replace it with hydrogen. And then they can do the reaction, do the oxidation reaction. And then basically, the iron 3 here will reduce into iron +2. And this iron +2 is already active enough for the reduction of nitro group. So we use this interface for the reduction. So it turns out this strategy is highly active for the hydrogenation of nitro group only for different kind of natural aromatics. So with this understanding, actually, during past several years, our group has tried to build up the pilot plan for making all these nanocatalysts by adopting our understanding, our concept. And many of these catalysts already been successfully applied in our industry in tons of scales. And with this, hopefully, I convince you that molecular mechanism understanding is really critical to achieve full controls over catalytic reaction involving with the use of a heterogeneous metal nanocatalyst, particularly if we want to get 100% selectivity, which is quite important in fine chemical industries because the regulation in China getting stricter and stricter. So if they want to make more money, they need to resolve this issue. So also create a lot of opportunities for us. So we hope that all this understanding can really move the design of those nanocatalysts from trial and error to rational designs. So with this, I would like to thank you all the funding agency for the support, and also so many collaborators and students who are working hard to make all this contribution. And thank you for your attention.
Thank you very much. Thank you very much, Professor Zhang. And any questions from audience? There are a lot of information, a lot of knowledge and fundamental understanding. And any questions? Well, I can start with one question. When you talk about, you deposit the palladium on copper, and when you deposit on copper 100 surface compared with 111 surface, and one has 100 surface give you much higher catalytic activities.
Right.
Although they all form the hexagonal packing, or not exactly. Now, what is exactly the reason they got a much higher?
Okay. Yeah, actually for 111 is hexagonal, but for 100 is a squares configuration, right? So in this one, actually, our DFT calculation suggests that because the difference in the coordination number, actually, they change the bonding strength of the reactant on their surface. So that's the reasons, and that's the main reason why we see the difference in their activities. So because the 1,1 surface is so condensed for the binding of this acetylene, phenylacetylene, so that's why it's not active for the hydrogenation, but for 100 surface. So
okay. Yeah. So it does not affect d orbital's orientation.
I think there should be something related to the d orbitals. So and of course we need to look at more details in their electronic structures. I think you point out a really interesting point.
Because for I don't know much about a catalyst, but my impression is all those catalysts related with those df orbitals. Mm-hmm. And if the d orbitals, one of them stick out, it's have much easier access.
Yeah, we will go back to analyze all our calculation result. I think because we only because the DFT calculation suggested that the difference in the assumption, but the nature behind might because their difference in their orbital orientation. That's possible. Yeah,
that is very interesting because that's all related with the bonding with the underlayer surface. So that's the hetero interface in inferences. Very interesting. Very well. Any questions from the audience?
I think it's too late.
Everybody is getting hungry and they are rushing for their lunch and in China. Thank you very much, Professor Zhang.
Okay. And thank you.
Yeah, thank you. Dr. Wang, do we have anything to say? And I wanted to say a few words. Tomorrow morning and tomorrow afternoon, we have a session number 2 and number 3. And Professor Yuri Gugusi will be the first speaker tomorrow morning. And the session 2 will start exactly, well, almost exactly the time as we started today. And session 3 will be in the afternoon. And I'm looking forward to see you all tomorrow morning in China time. And in the US, that's the evening time. And Dr. Wang?
Yes, thank you for all the speakers today. And welcome for tomorrow's session. We have 2 sessions tomorrow, chaired by Professor Huang Yu and Professor Wang Xun. So thank you again for all the audience.
Yeah, thank you for the speakers. And it is a wonderful talk. And Hongjin, you still want to sing a song? No, it's if you like entertain us, I will be here.
You know, the problem is once I started, I cannot stop.
Okay, we probably take next time. And thank you all. And we just close today's session.
Oh, okay. There's no session in the afternoon.
There's a session in this afternoon.
Okay.
Session will be in tomorrow morning and afternoon.
Great.
Thank you all.
Bye-bye.
Bye.
Bye.
Bye-bye.
桂林 ，can I ask you that？如果我